Good morning, guys, and welcome to the second session of this week. Just as a quick reminder, we don't have class on, thank you, Joseph. We don't have a class on Tuesday of next week because of the fact that this is an in-service day. The campus is closed. So we're not going to be able to have our meeting on that day, which is, and then we're not going to have a live session on Thursday because of the fact that's actually an exam day. So exam 2 is going to be on that day. So next week we will not be meeting. The next time we should be meeting is going to be on the 19th, which is basically the week after next week. So that's going to be our meeting, our live meeting. We're going to finish chapter 43 by then. I'm hoping to do that. I mean 42, why am I saying 43? 42. And thank you. And then also chapter, and then we start 43 by then. And we still have really 2 chapters after that, 43 and 44. 43 is a little bit kind of light to some extent because it's nuclear physics, although because there are only a couple of formulas that we have to deal with. 44 is a little bit more extensive, so we're going to get into it, and it's really more also descriptive than actually math heavy. So that is basically the last 2 chapters of this this course and this book actually. So this is basically the plan. Sounds good, everybody?
Yep.
Okay.
Sounds like a plan.
Very good. Here's the bad news, though. Okay, the lab is heavily, basically lengthy. Requires a lot of calculations. Okay. So, and I would urge you to look at it at least and do some of these calculations before the exam, because it's, in a sense, the lab is actually also an exam review. So it's really, really heavy. And there is also another requirement, fundamental requirement from the get-go that you guys need to be aware of. The lab has a, and I'm going to go on it, I'm going to go in detail on that, has an attachment which is a zip file, okay? And that zip file, that zip file is actually geared for a Windows machine. So if you really don't have a Windows machine, you have to be working with somebody who has a Windows computer, okay? So this is one of the things that you guys need to be aware of. And is there going to be a problem with this requirement? Do we have a lot of people using Macs in here exclusively? I mean, with a show of hands, I know you can use your hands on Canvas. Who only has access to a Mac in here from the people who are present right now? Only exclusively a Mac. So nobody. So we're in good shape then. So you can do this lab then. Because, and we're going to go through that, and I'm going to show you what I'm talking about. So there is that, that requirement that we have to have. And yeah, we're missing about half the class. So hopefully half the class will be showing up. So so this is not an issue. So I'm glad to hear that. Very good. Okay. So I'm glad to hear that this is not going to be an issue in terms of doing the lab. So that is one thing, and I will go in detail about the lab. So today the plan is to do part of chapter 42, and then the other part, which is really mainly semiconductor part, we're going to be dealing with it when we come back on the 19th. We finish that and immediately delve in chapter 43. So that's the whole thing. Sounds good? And I lost one of you guys who was in here, and for some reason he disappeared. And okay. Okay. So let me share with you the screen. continue with topic 42. By the way, I lost track of the weeks a long time ago, so I have no idea which week we are on. So I think week 12 or 13 or 11, one of those, because of the fact that one of them was actually spring break. So, yeah, well, I don't think so, Natasha. I think we are at least 12 or 13 because of the spring break.
Oh yeah, I think it's week 12.
One of them, I have no idea. I don't know. Okay. So let's continue this discussion on chapter 42, really. So we talked briefly about how the atoms rearrange themselves to form molecules. And basically, we're going to focus on diatomic molecules at this point and their physical characteristics, namely a diatomic molecule, for example, it's made up of two atoms. So it doesn't have to be of the same type. Like, for example, carbon monoxide, you have carbon on one side, which is an atomic mass of 12, and carbon and oxygen, which is 16. So in this case, it's not symmetrical. So this molecule forms a bond in here. So the other two electrons in here, they basically rearrange themselves. And you have a molecule that, among other things, it can rotate with respect to its center of mass. So this is the center of mass. This is the distance to one of them. So I'm going to label them, and they don't necessarily have to have the same masses, as in the case of the carbon monoxide, for example. Okay, so this distance, so this molecule is mass m1. I mean, this atom is mass m1, and it's situated at distance r1. And this molecule, this atom in here is of mass m2, not necessarily the same, situated at the distance r2 from the center of mass. I'm sure you did this in physics 1 a long time ago when you talked about the reduced mass. And we talked about it also when we talked about the corrections to the spectral lines that were off always by this factor of basically 1 to 2% from the experiment. And because it turns out that when we studied the electron going around in the case of the hydrogen atom, around the nucleus, which is a proton in this case, we used the mass of the electron, whereas we really should have used the reduced mass in the formula for the energy. And at that time, the corrections basically are lifted. So the reduced mass solves the problem. In most of the literature, we use for the reduced mass the symbol mu, which is the product of the two masses divided by the sum of the two masses. In this book, they use the symbol mr, okay? So this is the reduced mass. So it doesn't matter which symbol you like, it's the same thing. I think in physics 1, we use a letter mu. Okay, but now we have so many mu's. We have the dipole magnetic moment mu, we have the constant mu naught and the relative constant mu r. So there are so many mu's in the problem. So it's probably wise to use mr in this case and follow the notation of the book for the reduced mass. Okay, so what is this idea stem for? This object in here can spin, can rotate. So one part of it can go this way, the other part can spin this way. So it could rotate around two axes, really, around an axis. So I'm taking the center, the geometrical center, which is not necessarily the center of mass. It can take a center around the center of rotation, for example, in such a way on this axis or another axis also perpendicular to it. This rotation has a negligible moment of inertia I. As a matter of fact, I is equal to 0 in this case because they're supposed to be point particles. So I is equal to 0. So in this case, there is no kinetic energy associated with this case in here because the kinetic energy is going to be 1/2 of I times omega squared. And this I is 0. So that's why we only consider these two rotations in this case. And we discussed this one sometime in when we did also the specific heat a long time ago, the molar specific heats at constant volume, and we found it to be proportional to, equal to 5/2 times R, and the 5 is stemming from the fact that you have 3 degrees of freedom for the translation and 2 degrees of freedom for the rotation, and these are the 2 degrees of rotation. Here is something that you probably remember from physics 1 also, is that when I have a rigid body, and I'm asking that this rigid body can spin around some axis with an angular velocity omega. So this is the center of rotation, and actually this is the axis of rotation. So it can spin, I'm taking it counterclockwise in this case, it can spin in this fashion. There is a central, I forgot the name for it right now. I forgot the exact theorem name, but as long as it rotates with respect to any axis with an angular frequency omega, it will rotate with the same angular frequency omega with any other axis. And that is actually the condition of rigidity. Because, let's say, for example, if somehow I find another axis where it's spinning on a different value of omega, then in this case, there is a shift in frequency in here to lose the rigidity. In other words, parts are moving at different rates. Parts of the rigid body are moving at different rates. In other words, the separation between them changes. And if the separation between them changes, it doesn't matter if it's shrinking or increasing, then in this case, the rigid body is no more. It's not rigid anymore. So that is basically the point that we're talking about. That's why in this case, it's a good idea to treat the problem around the center of mass. So the center of mass, if you wish, is a preferred direction or a preferred place to take the axis of rotation. Because then we can treat the problem from the center of mass, and that's it. Once we know the moment of inertia with respect to the center of mass, we can use the parallel axis theorem. That's the one I try to remember. The parallel axis theorem. That basically says the moment of inertia around any center of rotation is going to be equal to that of, with respect to the center of mass, times m times the distance between basically the two centers squared. Do you guys remember the parallel axis theorem from physics 1? Yes. Okay. I assume that means yes. Okay. So that's basically what the idea is. So the center of mass is really a preferred axis to work with. And once we find the moment of inertia around that one, it's a good idea to work off of it anyway, because if you find another axis, all you have to do is just use this theorem and you have the moment of inertia around it. So the molecule in here, we're going to focus on its center of mass. And the center of mass in the center of mass reference frame is given by 0 equals 2. Of course, I have to take a direction now, so it doesn't matter which direction I'm going to take. So I'm going to take this one to be positive. So in this case, M1 R1, which is positive, minus M2 R2, because R2 is negative, it's clearly pointing in the opposite direction. So in the center of mass is 0. That's the origin, really. Okay. So this gives me condition on both M1, R1, and M1 and M2. I mean R1 and R2. Okay. So this is the separation of the two atoms from the center of mass, given by this condition. Furthermore, if I do a spectral analysis, for example, I really can find the separation between the two atoms. In this case, we're still dealing with a diatomic atom, a diatomic molecule, basically. Trying to get its mechanics. Okay, so the distance between them is R0, and R0 is clearly from the geometry is the sum of R1 and R2. I took them in the distances. Okay, so R1 and R2 are distances. So don't tell me that it's R1 minus R2. That doesn't make sense because I took it already R2 as a big positive, and I accounted for the sign in here. So these are two equations that I can solve for R1 and R2 in terms of R0. I need to find them in terms of R0 and the two masses. Obviously, in this case, the two masses are known. Don't forget that this is times the unit mass, which is 1.6 times 10 to the negative 27 kilograms. So I have to multiply the atomic masses by this number to get the actual mass of the atom. okay? Or in the case, the atom mass of the atom. But the thing with it is, also don't forget to add the mass of the electrons. So I really should multiply it by the mass of the hydrogen atom, okay? And then at the end, multiply that by 16 or whatever number the periodic table is giving me. So it's really, if I am looking for a specific isotope, I have to multiply by that isotope. If not, then I go by off of what the periodic table is giving me. And for the case of oxygen, it's giving me exactly 16.00, whereas for carbon, it's 12.01, okay? Anyway, at least this periodic table that I'm using in here. So we need to solve this equation for R1 and R2. Obviously, this equation already gives me one of them in terms of the other. So I'm going to get M1 over M2 times R1. Plug it into this equation. So that becomes R1 plus R2, and R2 is M1 over M2 times R1. And this gives me R1 in terms of the two. So the common denominator is M2. When I flip it on the other side, it's going to be in the numerator. And this is just the sum of the two masses, M1 plus M2 times R naught, which is the distance between the two atoms. Same thing, similarly, I can find what R2 is, and using this equation, I multiply by M1 and divide by M2. That cancels M2 from the numerator and leaves M1 by itself, divided by M1 plus M2 times R naught. So this is the two values, and I need them because I need to find the entire I, the moment of inertia, for this molecule. And the moment of inertia is just the sum of the two moments of inertia for the two components, which are 2-point particles. Each and every one of them is at a distance R1 or R2 from the center of rotation, which is happen to be the center of mass, okay? Obviously, the whole point of this exercise is to express them in terms of R naught, not in terms of R1 and R2, okay? Because we don't have access to that information. We really need them in terms of the separation between the two atoms, how far apart they are, okay? So 1/2 is a common denominator, common factor, but forget about that for a moment. I'm going to express R1 in terms of R naught, and I'm going to express R2 in terms of R naught from that expression that I just found. So this gives me I equals to 1/2 of M1 times this number squared, which is M2 squared divided by M1 plus M2 squared plus times R naught squared. So the 1/2, by the way, and the R naught squared is going to come out. So I'm going to be left only with this mass terms in here. So times M2 times, again, this number squared, which is M1 squared over M1 plus M2 squared. It turns out that also that the common denominator, the denominator is common between them. So I could pull that out too. So basically, I have the answer then is 1/2 times the common denominator, which happened to be M1 plus M2 squared. And then in the numerator, I have M1 times M2 squared, and I have M2 times M1 squared, which is a common term in here is M1 times M2. And I'm left with an M2 from this side. And I'm left with an M1 from this side. And of course, times R naught squared. So we did that quickly. Obviously, one of these powers cancels the one term in the numerator, and I'm exactly at the reduced mass. So this looks like 1/2 times MR I naught squared, where MR is equal just M1 times M2 divided by M1 plus M2. As a matter of fact, we write it differently usually. We say that MR is the inverse of the sum of the inverses. So this is the reduced mass. That's why in the case of the proton and the electron, the main contribution was coming from the electron because it's a much, much less term than that of the proton. The proton is almost 2,000 times bigger. So when you invert a big number, it becomes small. So the contribution of the proton was tiny compared to that of the electron. The electron was smaller. When you invert it, it's bigger. Of course, you're going to invert the inversion. So at the end, this is the main contribution is coming from the electron. So if this term is, let's say, for example, a factor of 1, and this term is a factor of 2000, obviously the 2000 is going to be ignored. It's practically 0, and this factor is inverted. That's why the mass of the electron appeared in the calculations, in the spectral analysis in there. So in this case, the mass actually should be shifted closer to 12 for carbon monoxide if we're going to take that carbon monoxide, because it's the smaller mass. So the reduced mass should be closer to 12 than 16. This is similar to what you guys have done for resistors in parallel. Resistors in parallel, when you put them together, the equivalent resistance is going to be smaller, closer to the small one, rather than closer to the big one. Okay, so the small one will always contribute higher. And actually, it's going to be slightly less because I put 1 in here. It's going to be less than that. But that's basically part of the properties of the reduced mass. So here is how the problem then. Instead of working with this molecule, we're going to work with a different system altogether. We have a center of rotation here, which happen to be the center of rotation, which is different than the center of mass now. And we have a mass that is a reduced mass, and oscillating at a distance are not, or rotating at a distance are not from the center of rotation. So this problem is completely different because this is its moment of inertia now. Okay, where R naught is not R1 or R2. It's the separation between the two atoms. So this is how the system works. It works as just one unit. The whole molecule now is behaving as just one unit around the center of rotation at a distance R naught from it. And the mass is that of the reduced mass. So now, having said that, the angular momentum associated with this one is going to be quantized without going through the details of it. Quantized, okay? And it's going to be the angular momentum, of course. And the energy at the end is going to be the angular momentum squared over 2I. So this is the energy, because it's a free particle in this case. Free molecule. That's how we're treating it now, as a free particle, because we're only concerned about its rotation. And its energy is going to be equal to basically the value of the angular momentum squared divided by 2I. Similar, in a sense, to this expression. Okay? Obviously, I omega is what I meant by it to be the angular momentum. And that is the classical version. And the kinetic energy in this case is going to be L squared, which is I squared omega squared, but I have an extra I squared now, and that I need to cancel, and that's why I bring the I downstairs in here. Okay? So that's basically what we have in this case, except that I have to quantize this thing. I have to write it in quantum mechanics. So the energy at the end is going to be L times L plus 1 divided by 2I, and this one is h bar squared, because L the magnitude of L is square root of L plus L1 times h bar. So that is basically the expression that we end up for in this case, where I is that value that we have in there. So the energy levels in this case, if I have a diatomic molecule, and if it is excited, it's going to rotate. And it's basically the quantized energy level. Obviously, the lowest value is L equals to 0. And L equals to 1, and so on and so forth. So the lowest value is L equals to 0, L equals to 1, which gives me the magnitude of the vector, which is square root of 3 times h bar. No, it's the square root of 2, I'm sorry. So this is L equals to 1, this is L equals to 0. So this is E equal to 0. So the energy in this case is going to be 0, and the angular momentum is going to be 0. The angular momentum in here is going to be square root of 1 times 1 plus 1 times h bar. So it's square root of 2. And then square root of 2 times, for L equals to 2. So it's going to be square root of 2 times 3, which is square root of 6 times h bar, and so on and so forth. The separation are not constants, okay? So this is square root of 2 times h bar, and this difference is actually square root of 6 minus square root of 2 times h bar. But this is the energy levels now are quantized when we take quantum mechanics into account. The energy, it should really be the kinetic energy in this case should be just the angular momentum squared divided by 2I, and the angular momentum itself is quantized. Okay. So what is that term is coming from? It's coming from actually the expression that we talked about last time. Times the function psi. And this is basically, don't forget you have a negative h bar over, in this case, 2m, and plus is equal to E times psi. So this is Schrodinger's equation. You take this expression and you convert it to spherical coordinates, x, y, z, going to r, theta, and phi, where r now is constant because the molecule, the only thing it can do is just basically spin around this axis. As a matter of fact, r is equal to r naught. So you'll be left with these two terms in here, okay? And those two terms, this is, by the way, called the Laplacian operator. And these two terms derive something called the Legendre function, Legendrian, which is just the reduced version of the Laplacian without the r, because the r is constant. Any derivative with respect to r is equal to 0, because r doesn't change. So the only thing that remains is the derivative with respect to theta and phi. And then once you solve that, they are going to be exactly the hydrogen atom solutions without the R in them. Okay. And those solutions, they satisfy this equation in this case. And L can go from 0 to whatever value that you would want. There is no end limit on it now. Okay. So it can rotate with any value of the angular momentum it can. When L is equal to 0, in this case, the molecule has a spherical shape. I mean, the wave function distribution has spherical shape, not the molecule. The molecule itself is just a linear diatomic structure. Okay, so this is the energy level now is quantized. Makes sense, this value and how we got it? So the energy in this case, so let me write it down, depends on this index L, and it's equal to L times L plus 1 divided by 2I times h bar squared. So that's the bottom line of this whole argument in this case. This is a pure rotation of a diatomic molecule. I, in this case, is equal to 1/2 times the reduced mass of the two atoms times the separation between them squared, where MR is just equal to the product of the two masses divided by their sum, the reduced mass. Make sense, everybody?
Yep, makes sense.
Okay, very good.
Yep.
So we dealt with this part, and hopefully it's not hard enough for you guys to follow it. The other part now, again, look what we do in physics. We separate the problem. We try to solve them basically one problem at a time. Namely, the second part of the diatomic molecule is its own internal vibrations. So basically, I could model now this two atoms. Still, you can take the carbon monoxide. You don't necessarily have to take the oxygen and nitrogen, similar atoms, just to give you an illustration of this things in here. So there is a spring constant in here. Okay, we have so many K's also in here. Okay, which K we're talking about? Okay, we have K for the wave number. We have K, which is insisted to put the index B on it permanently. In some other literature, they don't, especially when they are doing thermodynamics only. Sometimes they put the lowercase b. I put always the uppercase B. And that's the Boltzmann constant. That's 1.38 times 10 to the negative 23. The units for it are energy, which is joule per Kelvin. Okay. And so this is the wave number. And then we have this K now, the spring constant. The book just puts a prime on it. Okay. So we could follow the convention of the book, and here this is the spring constant. So that we're not confused which K we're talking about. Okay, that's all. So this is the spring constant basically. So what I'm modeling in this case is any vibration is governed by this one. So really, I have one mode of vibration in this case. So this can be in, and this is in, or this one is out, and this one is out, because they cannot be both. They cannot be both. One of them is in and the other one is out, because then that amounts to translation. Okay, so if I do this, then the whole center of mass is shifting. That's all. Okay. So this is really not an interesting, because that's just a symmetry in the translation, which brings me back to the moment of inertia, to the regular momentum, the linear momentum, because that's part of the translation. Okay. Anyway, so these are the two modes, and they are the same actually. Those two are the same, because as the molecule, the atoms get in, they get out, in and out, in and out. So this is basically the vibrations. Again, we can treat the problem around the center of mass. And also there is a similar treatment in here, because remember, M1A1 is equal to M2A2, because this is a free system, and any interaction that is coming, that's giving me this free constant, is under the obeying the third law of Newton in this case, which is F12 is equal to F21 in magnitude, but they are opposite in sign. That's basically what this thing is. So at the end, the M1A1 is equal to M2A2. And if I treat the separation between them as again being R1, and this one is being R2, and therefore A1 is the second derivative of R1 with respect to T, and A2 is the second derivative of R2 with respect to T. And again, introduce the center of mass, the separation between the two atoms in this case being R1 plus R2. And if I follow a similar analysis, the problem reduces to that of the reduced mass also. So that's why in this case, the omega is going to be equal to the square root of this K prime over M. In other words, the problem is replaced by spring attached to a mass, and the mass in this case is the reduced mass. Okay, and if you are wondering about the acceleration, the classical system at least, so we always go back to the classical system to try to find the physics behind it, and then we generalize the idea to quantum mechanics. So this is the spring constant K, and this is MR, and at the end we're basically finding omega. So this is omega that comes up from the classical system. Okay, so now this is the harmonic oscillator, and it's governed by this potential, which is in this case equals to negative K prime, or potential is K prime, times the separation, in this case, delta R prime, which is going to be R naught squared. So this is the potential where we're going to treat the system, except this R now is changing really, okay? R naught is the separation when they are both fixed, and R is their separation when they're vibrating. So it goes in and out, okay? So the potential energy in this case is quadratic. And we solve Schrödinger's equation in this case, and becomes just a one-dimensional problem. And the energy in that case is going to be quantized, and it depends on an integer n. This is not the quantum number that the principal quantum number for the hydrogen atom or for the atoms, but we're treating the system now, which is a molecule, as being a harmonic oscillator. So the value of the energy is quantized, and n can be equal to 0 now. This is the ground state, plus 1/2 times h bar omega, where omega is given by that expression. So if I know somehow the strength of the interaction of these molecules in here, I can find their energy of the vibration in this case, even for n equals to 0. So n equals to 0, 1, and so on and so forth, 2, and so on and so forth. So the energy in this case for the harmonic oscillator, because that's exactly what it is going to be quantized, and the units of quanta are going to be h bar omega. In other words, when the molecule goes from a transition from an energy level to an energy level, the difference between two of them, namely delta En, is going to be governed by n plus 1 plus 1/2. That's the higher energy level. I'm going to treat the emission, okay? So I'm going to assume that the final state has a lower n. So n plus 1/2 only, that's the lower one, is equal to, obviously everything cancels except 8 bar omega. So this is the quanta of energy in this case. that we're going to have for this vibrations, okay? So the vibrations are associated with this much energy with them, whereas in the first case, the difference in energy is going to be from L plus 1 times L plus 2 times h bar squared over 2i minus L times L plus 1. So it's going to give me 2 times L plus 1 times h bar squared over 2i. So that is in the case of the emission again. In the case of the absorption, the final state will be n plus 1/2, and the initial state will be n plus 3/2, and you do the subtraction. Okay, so that's an absorption. This one is an emission because I would want to find the frequency of the photon that is emitted. In general, though, and this is the main thing, in general, for a molecule, it can do both. It can rotate, and also in the same time, it can vibrate. So in general, the energy is governed by 2 quantum numbers for the molecule. And these 2 quantum numbers are the one coming from the vibrations and the one that is coming from the rotation. L times L plus 1 divided by 2i times h bar squared, okay? Where in this case, I is equal to 1/2 of mr times I squared times r naught squared, and also omega is equal to square root of k prime, the spring constant equivalent of the system, divided by mr, where in this case mr, in both cases mr is a reduced mass. Okay, the problem gets complicated with triatomic molecules and more, because you have to really get the so this is the bottom line. Okay, so these are the energy levels for a molecule, not an atom, and it's characterized, as I was saying, by the vibrations and also the rotations. Okay, the frequencies usually are a lot lower than of the photon that is emitted when the molecule transitions from one energy level to a next energy level. Remember, if there is an emission or absorption of a spectrum, always delta L in that case must be equal to plus or minus 1, because the photon emitted must carry with it an angular momentum, and it's either going to be polarized one way or polarized the other way. So delta L must either increase by 1 if it's polarized to the left, or if it's a right-handed photon, it has to be, in this case, decreasing by 1, okay? So this is basically what I mean by that, is the way that the photon is coming out. It's going to be circularly polarized. Is there going to be a counterclockwise or clockwise, whichever one comes in? It doesn't matter at the end. Delta L must either increase by 1 and decrease by 1. This is the selection rules for the molecules in this case. We're not going to get into the more complicated situations, because the geometries get even more complicated and more terms get introduced. And honestly, the contributions start to become smaller and smaller. So let's look at a couple of examples from the book. Okay. And then we get into the general idea of how solids are working. How much time? We still have good time. Good. So the 2 examples that I want you guys to pay attention to are 42.2 from page 1412. And that example basically gives you the carbon monoxide, again, the one that I was talking about it in here, and gives you the masses of the 2 molecules. First of all, for the carbon, it's equal to 1.993 times 10 to the, because we really need those masses, okay? 26 kilogram. And for the oxygen, it's 2.656 times 10 to the negative 26 also kilogram. So from here, you can find MR. Just take So it's going to be 10 to the power 26 anyway, negative 26 anyway, kilogram. And the only thing in here is 1.993 plus 1 over 2.656 raised to the negative 1 power. So this is going to be, I'm going to trust that the calculation is correct. So you guys need to verify that too. So it's going to be 1.139 times 10 to the negative 26 kilogram. Again, it's closer to that of the carbon in this case, and it's usually less, as I was saying, because of the properties of the inversion in here, that's all. This is just like the resistors, okay? So this is a reduced mass, and they also gave you the separation between them. They said that R naught, the separation between these two, is 0.1128 nanometers. And this number is important because you guys need to understand that when you are forming a molecule, they get very, very close from one another. Okay, there is actually an overlap of the outside wave functions. And that's how the bonding happens actually between them. So the separation between them is 1.128 angstrom. So this number is very important to remember, that the sizes we're talking about. They're extremely small. So we have everything in here, and they said in this case to find the wavelength of the photon emitted in the transition from L equals to 2 to L equals to 1. From L equals to 2 to L equals to 1. Obviously, all we have to do in this case is find the energy in this case, which is going to be equal to, first of all, is this allowed? Yes, because L is decreased by 1. So this is fine. So in this case, you find the expression for both of them. And you need to find I, that's all, which is in 1/2 of MR, which is this number, times I naught squared, which is this number, 0 or 1.128 times 10 to the negative 10 meters. So when you square it, it's going to be 10 to the negative 20 meters squared. And when you multiply it by 10 to the negative 26, it's going to be 10 to the negative 46 in the denominator. But each bar squared is 10 to the negative 34 squared, which is 10 to the negative 68. So 10 to the negative 68 and 10 to the negative 46 is going to be still a tiny number. That's the bottom line in here that you need to remember from this ratio. That this is going to bring you 10 to the negative 68, and the denominator is going to be 10 to the negative 46. So overall, is going to be 10 to the negative 28. All granted, there are some factors in here of or the order of 1 that are going on. You have 2 times 3, and here you have 1 times 2 divided by 2, and you have this factor in here that is squared for the denominator and multiplied by this factor in here in the denominator, and you have the h bar squared in here. Is it? Oh yeah, 22. I'm sorry. You're right. Thank you very much. Okay. Thank you very much. Okay. So, and then we need to convert it into electron volt, which is 10 to the negative 19. Don't forget, you have 1.6 times 10 to the negative 19. So the bottom line in here, this will be of the order of 10 to the negative 3 electron volt. So the expression in here said to express it in milli electron volt. So it's a tiny number. It's a tiny number. So that's the difference in the energy. It's a tiny number. That's why the wavelength, because you're supposed to find, so this is going to be the energy of the photon, by the way, which is hc over lambda. The photon is going to be the difference between these two energies. So lambda will be a big value in this case. As a matter of fact, it should be in the microwave region. So if you're going to do a spectral analysis, don't bother yourself with the visible light or the X-ray or anything like that. You're way on this side now. So you have to be looking in wavelengths that are higher. Make sense?
Yes.
Yep. Okay, very good. Okay, very good. So now the follow-up on this example is actually on the next page or the next two pages, 14, 14. And that tells you consider the molecule from the previous example, find the wavelength of the photon emitted by carbon monoxide molecule when its vibrational energy changes and its rotational energy is initially 0 and finally 0. So here is the deal. When it's initially 0, so when L is equal to 0 initially, and the only place we can go is L equals to 1. So initially 0, that means when I'm calculating this energy, the initial value is 0, the final value is 1. So whatever comes in from here, it's easy. It's going to be h bar omega no matter what. Okay, times however the separation. But we're saying in this case, it's just 1. Okay, so it's going to be h bar omega. Okay. Did they give us the value of oh, I'm sorry. They gave you also the value of K, which is 1.9 times 10 to the power 3 in this case, which is a big, strong value. Okay. Newton per meter. So it's 1,900 Newton per meter for K. And that is actually from the previous example. In other words, just follow the values in here. So you can find omega, which is just the square root of that 1,900 Newton per meter divided by, again, MR. Okay. In MR, you found it somewhere in here. Okay. So you have omega. You can find what the delta E is. So again, just to set up for the example so that you guys are aware of it. So if the initial state is L equals to 0, the final state can only be L equals to 1. It cannot be any other value. And they said if the final value is L equals to 0, so this means that delta L is positive in this case, positive 1, because the final minus initial is so if the final value is 0, it can only be L equals to 1, the beginning, the initial state. So in this case, delta L is equal to -1. Okay. And it's an emission because if you look at the problem, the way that it's said in here, a photon emitted. So the energy of the photon at the end is going to be a positive value, but one of them will have a higher energy than the other. Both of them will have a photon emitted, but one photon will be a longer wavelength and one photon will be a shorter wavelength, and the shorter wavelength will have a higher energy than that of the longer wavelength, and that's the end of it. So when you look at the spectral analysis and you're looking at lambda, and lambda, you left the visible light way on this side, so lambda is increasing on this side. So this one will correspond to the shorter, the longer wavelength, which means that you have a value of omega that is less than this value in here, the transition on this side. So that's basically what you're looking at in terms of spectral analysis. I think with more examples from the problems that hopefully you guys will do, you should be in good shape for this part of analysis for molecular vibrations. And like I was saying, triatomic molecules and other molecules, they get a little bit complicated because those modes of vibrations now you introduce more, okay? You introduce more because in the case of triatomic molecule, the middle can be sitting still, especially if they are symmetrical, like carbon dioxide, for example. You have two oxygen on one side and the carbon is in the middle. So in this case, you can vibrate in and out, or you can vibrate up and down, or you can vibrate basically out of phase, where the two oxygen atoms move one way and the carbon will move opposite to them. So basically, the two molecules will be in phase, oxygen and oxygen, and the carbon will be in the opposite direction. Okay. The problem, even in the classical mechanics, and I know I did this class, I taught this class several times in the past. I mean, the classical mechanics, not talking about the quantum version of it. And when we try to find the modes of vibrations, the problem gets a little bit complicated. There are different ways of tackling it. One of them is actually using matrices and find where the determinant is 0. And the solution for that will give you the different values of omega. And you go and place them back on the problem and you find the actual vibrations that I was describing. Okay. Even in the case of the linear geometry, where you don't have the molecules are coming in and out of shape, you will have basically the mode. First of all, the translation that's going to be there. That corresponds to omega equal to 0, because in translation, in this case, the whole molecule will move one way or the other, including the middle, the carbon. Or there are two other modes in this case, where the carbon will sit still, doesn't move at all. So in this case, the oxygen will come in and out, basically, and the carbon sitting still. The center of mass doesn't change. Or the center of mass also doesn't change in another mode, where the two oxygen molecule will move one way, and to compensate for it, the middle one, namely the I thought I can model these things in here. Okay, so imagine this is a rigid structure. These are magnets, by the way. But if I try to break them, these are strong magnets. Okay, so these two oxygen molecules will move one way. And to compensate for them, the carbon molecule will move in the opposite direction in such a way that the center of mass doesn't shift, stays in its place. Granted that the carbon molecule atom is slightly smaller than the other two. As a matter of fact, physically, it's probably slightly bigger, but in terms of mass, it's slightly less. Okay, so they shift in and out. Okay, so those are the three modes. One of them has a 0 frequency in this case, but the other two will have a definite frequency. So thus the 1,0 is just translation, so forget about it, meaning the center of mass shifts with them. The whole thing is just moving one way or the other. Now, if you include the fact that the molecule can get in and out, then the problem becomes even more complicated, okay? So this is why we only focus on the diatomic molecules in this case. Sounds good, everybody? So that's what you're going to be tested on, diatomics. Yes. You guys have any questions so far before okay, let me tell you what I'm going to talk about next before we get into the energy bands. Just going to talk briefly about the structure of solids, okay? And you probably have seen that in chemistry too. So what I have in this case, I have a molecule inside, the one that you see it in green in here, not a molecule, I should say, an atom, okay? And I have, in this case, it's called a body-centered cubic because it's a cube, and in the middle, it's also, it has an atom in there. You could potentially have another atom in here and move the whole shift, basically shift the whole thing in a different configuration and have it there. So this is a common structure. Common structure is that there is a body in the center and the other molecules sit. So this is a crystalline structure. So when materials crystallize, they crystallize in this one. It used to be, people used to believe that metals cannot crystallize, but now we know that they do. They are not amorphous, actually, they are crystals too, okay? So this is one way. So when the atoms start to come together, they pack just like this magnetic material that I have in here. They start to align themselves as close as possible from one another. So this is one thing, one configuration is the body-centered cubics. So it's called the BCC. The other one is an FCC, face-centered. I couldn't do this with this one in here because of the magnetism, that's all. But every face in here, you will have a molecule in here. And this repeats, an atom, I'm sorry, why am I saying molecule? An atom, and this repeats throughout the whole cycle. So you could have a BCC, body-centered cubic. You could have an FCC, a face-centered cubic. There is another in common structure, which is a simple cubic, which does not have any external base. So it's just basically 4 atoms sitting basically, not 4, 8 in this case, sitting in the corners of a cube, okay? Or you could have, what is that? A hexagonal closed pack, which is an H CP, okay, which is basically a packing in a different configuration also. Those are the three most common, but they are more than that. I mean, if you look at the geometry itself, it's a little bit more complicated for a lot of materials. One of them, which is going to be a big concern to us down the road, namely the diamond structure, okay, which is just the atoms are shifted a little bit with one another in cubic structures, okay? And that diamond structure is a very, very stable one. I mean, one of them is diamond, of course, carbon, basically, atoms aligning themselves in such a way that it becomes the most sturdiest material out there. And that is where the structure is named from. It's how the carbon atoms align themselves to be called the diamond structure. And that's going to be important because that's also how germanium and silicon also arrange themselves. And it's that diamond structure that's going to lead us to the semiconductors, okay? So that is in terms of how atoms pack themselves up. We still have a good 20 minutes or so before I introduce just the concept, okay? We're not going to be doing calculations in here, namely the concept of the band structure. And then next time we probably are going, when we meet, which is going to be the 19th of the month, that is when we're going to get into the little bit more intricacies of this thing in here. Okay. The band structure was suggested by Fermi, and later on, basically, all kinds of work came from it. So here is the idea. When you bring two atoms together, obviously of the same type, for example, germanium, iron, it doesn't matter. The atoms themselves are identical. So what happened in this case, they have the same energy levels. But if you start packing them next to one another, they cannot be in the same energy level because two electrons that are sitting on that energy level cannot be close enough from one another. So what happened in this case, the energy levels start to shift because of the packing, okay? So start to shift, one slightly below and the other one slightly above. Obviously, I don't have two atoms in a metal or a solid object. I have a lot of them, usually of the order of 10 to the power 23. So this, as I start to force them closer and closer from one another, they shift just in a fashion, although it's discrete, but when I'm looking at it from above, it looks like it's a continuous distribution. Looks like it's a continuous one whole level where the atoms used to exist. So this is called a band. Okay, let me illustrate it a little bit in here so that we have an understanding of what I'm talking about in here. So imagine with me, where is the pen? Imagine with me, I bring a lot of, okay, atoms that are, all of them have the same energy levels. So this is not just one atom. This is an Avogadro number of them, but they are far away from one another at this point. They are all at the same energy level. So they are indistinguishable from one another, obviously far away from each other, meaning that the electrons can sit there comfortably with no problem whatsoever. This is the outer layer, of course. That's the one that is concerned with chemistry and solid state physics. The inner layers, they don't get bothered at all in this way, okay? So this is where the so-called valence electrons are sitting. So now when I bring them together, now this energy level starts to split. And the more I bring them together, the more splitting is going to happen. Some of them are going to be slightly above, and some of them are going to be slightly below. And the electrons, so this is, if you wish, the separation between the different atoms. Oh man, I cannot draw a straight line on this thing in here. I'm supposed to draw a straight line in here, trying to at least. Okay, and so this is the energies. So far away from one another, the energy in this case, it can be all of them the same. There is no problem with Pauli exclusion principle. When you bring them together because of the exclusion Pauli principle, in that case, they cannot be, they cannot stick together. Same thing for the next higher level. So these are the valence electrons. These are the outer ones. Okay. The one that they can get excited to also is going to be split and becomes available for them if they need to jump to it. So also the next energy level also, which was also a straight line, in a similar fashion starts to split when you bring them closer to one another. And there is an overlap at some point between these two energy levels. So these are free atoms. They're separately far away atoms. Okay. It's like a gas state in here, if you wish, or a liquid state for that matter. When I bring them closer and closer to one another, at that point, this is a distance where I have clearly two energy levels in a band. Obviously, in this example, I have a big separation between them, a huge separation between the two bands. It requires a lot of energy for them to jump from this level, from where they are actually bound, they cannot move, even though you have a lot of energy levels in here, but technically they cannot really move those electrons because you require so much energy to have them in this region, which is free of electrons at this point. Okay, so you need a lot of excitation to get them there. So in this case, and we will see this one is actually a case of an insulator. When they are in the case when there is an overlap between the bands, with a little bit of electric field, if you wish, the electrons that were in here will find the space where they can jump in there and can move at ease. So this is the case of conductors. Even as a matter of fact, with a little bit of temperature, they can find themselves free to go. So at 0 Kelvin, they will not be able to move because they will be actually in the valence band. But there is an overlap at some point in here. They're actually free. They're completely at room temperature. They're completely free from their own atoms. So in a sense, it's like a free gas of electrons. The actual solid in this case is still neutral. So there is no charge overall. Because yes, they are free from their individual atoms, and each atom will contribute the same number of electrons. But it's still, there is a total charge that is equal to zero in this case, because yes, let's say, for example, you gave up 2 electrons to the gas. So you're left with 2 positrons in here. So at the end, the overall charge stays 0. So when this one of the electrons wander away, another one comes in to replace it from the next door neighbor, and so on and so forth. So the gas, I mean, the actual material itself is neutral. So if you take a copper wire, for example, and you touch it, you don't get electrocuted because of the fact that it doesn't have a net charge. So the net charge is still 0. Yet in this situation, there are electrons that can move at will. With a tiny electric field, they can move. So this is the case of conductors. This is the case of insulators. There is in here a class of materials where the gap is not that big between the valence bond, this is called the valence band, and this is the conduction band. There is a class of them called semiconductors. So a semiconductor has a small gap between the two. With a little bit of temperature, some electrons will find themselves. Remember, the energy is proportional to the negative of 1/2 of mv squared over kBt. That's what we saw last time when we did the chapter 18. This is their kinetic energy. I'm treating them classically. Obviously, I need to fix that now since we're doing quantum mechanics. And but the point being in here is, with a small increase in temperature, this factor in here can give them enough velocity. As a matter of fact, the velocity distribution, they will have enough velocity to be here. So with a proper electric field, they can conduct electricity. But here is the thing though. If an electron moves in here, and it's actually in the conduction band now, it will leave a gap where it was, and that gap is called a hole. Okay, so that is a hole. Okay, and this is an electron. So let me, we'll still have good time. Okay, let me give you a little bit of an idea where the hole came from. when we do the energy, when we go and solve Schrodinger's equation, and when we find it, we find the energy level that corresponds to a certain wave number have two values, one above the x-axis that seem to have a positive mass, and one in the below the x-axis, below the x-axis where the k actually is, that is actually negative. So we think that, hey, there is a negative mass. So instead of talking that we have a negative mass, we have a missing mass, if you wish, of an electron. That's exactly what happened in this case. It's going to be equal to that of the electron. So we are missing electrons. That is the one that is going to be responsible for the conduction of electricity. So we call those holes. And they're positively charged because we are lacking, in this case, an electron. So the charge in this case is positive. So what's going on in reality? In reality, the case of the semiconductor, what's going on in this case is the ion is fixed, but somehow one of its electrons, the one that was supposed to be neutralizing the whole thing, ended up free to move. And it's actually going and moving on its own. Has nothing to do with the structure now. So now it has a net charge of positive charge. And a positive charge in this case can move in the following way. Here is what's going on. Let's say, for example, I apply an electric field in this direction. So E is in this direction, okay? So there is a hole in here, and there is another hole in this next door neighbor. So an electron jumps to fill out this gap. And because of the electric field, remember the electric field is opposite to the charge. So there is still remnant of electrons in this case. So another electron will move, the same electron will move in here under the same effect to fill out this gap and fill out this is equivalent to saying that the hole actually is moving in the same direction as that of the electric field. Whereas this electron in the conduction band, that is going to respond to the electric field anyway. So the one in the electron by itself, that's going to respond to the electric field and move this way anyway. And it's going to move in the opposite direction, resulting in a current that is going to be in this direction. Remember, the convention for the current is going to be moving against the electric, where the negative charges are moving. So the negative charge of the conduction band will move in this direction because we applied an electric field in this direction. And the holes are actually going to move in the same direction as that of the electric field. And the electrons are going to be moving in the opposite direction, both of them resulting in a current that is in the same direction as that of the electric field. So there are two charge carriers in this case, two things responsible for conductivity in a semiconductor. You have the holes and you have the electrons. The holes and the electrons are negatively charged, so we call them an n-type carrier, because they're negative. So N stands for negative. So they're negative charge carriers. Whereas the holes in this case, if you want to, you write them usually by E+. It doesn't mean it's a positron, it's just a hole. They're a p-type carrier, p-type charge carrier. And both of them work together. I mean, to conduct electricity, P stands for positive. Okay. So this is the essence of semiconductors. So when we meet again, we're going to try to have an explanation for conductivity in here. We introduce two things. We introduce the state density and function, okay, G of E, which gives me how many states available for the electrons to occupy, basically per unit energy. That is this value. We're also going to introduce the Fermi-Dirac function, which is a distribution function, which gives me the requirement of how electrons will occupy an energy, okay? And then multiply the two of them, we're going to find how electrons are distributed in a metal. And we have an explanation for metals. We define at that point the energy Fermi level, EF. And we will find that the energy Fermi level in the case of equilibrium for a semiconductor is sitting just in between the two bands, the conduction band and the valence band, and how doping will help shift that energy level, okay? There is an N-type doping for semiconductor silicon or germanium in such a way the predominant charge carriers become the electrons. And there is a P-type doping, basically of, again, silicon and germanium, so that the dominant actually charge carriers become the holes. And this mechanism, the way I described it, not electrons anymore. And so you have a P-type material and an N-type material. We put them together, and now you have a diode. Okay, that can conduct electricity only in one way, not the other way. So it can be used in logical systems. As a matter of fact, you can put two junction of two materials and put them in a PNP junction, and you have the so-called BJT, bipolar junction transistor, which is a typical transistor now that is used in the industry. Or you can have an N-type material connected to a P-type material to an N-type material, and you have an NPN BJT also. These are one type of three types of transistors used in electronics. The other two types are the MOSFET, and there is the other type that is a hybrid really between a MOSFET and this type of transistors. All of them are used in two applications in electronics, either for gain of a signal that is too weak, like for example amplifiers and microphone, or actually for logical systems to basically tell you it's a 0 or 1. If you open your phone, you will see that the processor for it is made up of billions of this type of transistors, or the other ones, the MOSFETs, or a combination, as I was saying. Okay, we're not going to be dealing with the MOSFETs in this case. Okay, that's not the one. So we're going to just focus on the bipolar junction transistors because they're easier to understand to some extent. And that's going to be the end of this chapter once we cover these materials in there. Okay. We're going to talk with nothing at all about superconductors. Their mechanisms is not related to neither of this. Okay. There is a different explanation for superconductors. We're going to talk about them, and that's going to be the end of the chapter. Sounds good, everybody?
Sounds good.
Okay. So I don't want to jump in the lab yet. So what I want to do is, we want to take a break for about 15 minutes. And the lab, as I was saying, is a long lab. So I want to take about 15 minutes break. Right now it's 9:12 according to my watch. So we should 9:13, just jump to 9:13. So around 9:30, we should meet back again and basically focus on the lab, because the lab has two purposes. First of all, it helps you prepare for the exam. It helps you in a sense also understand the topics more. And also, it's an important lab. You get grade for it, so you have to do it. Okay. So we have good incentives for it. Sounds good.
I have a question really quickly. Are we going to be doing any exam review by any chance?
I asked last time if you guys have any questions about that. Honestly, that coverage should be ample. If you have specific questions about them, so I suggest you go through the examples we did in the class and also the stuff. So I can follow up with a communication basically about the things that I think are important for you guys to review. So I can do that today in the afternoon. I will send you guys a message, the things that need to be focused on, because the chapters are 37, 38, 39, and 40. Okay, definitely the tunneling. That's one thing, okay, that's important. Also relativity and Lorentz transformations, so that's another one that you guys need to focus on. And the expression that we wrote it several time again, namely HC over lambda or the omega, or lambda is the one that is basically how you get P out of that. So out of lambda. And the other thing that is important is the competence scattering. Actually, it was part of this units also, so part of these chapters. And there is an important topic that now it's skipped my mind. The selection rules, of course, for the, no, I think the selection rules are for the next exam. They're not for this exam. Oh man, there is another topic. So I mentioned the Lorentz transformations and the energy equivalence from chapter 37, Compton scattering, and de Broglie expression basically, and the quantization of the energy for the case of the infinite wall for a one-dimensional problem. That's actually problem chapter 40. I mentioned the tunneling, which is extremely important. Okay, from that chapter. There is another topic. It's slipping my mind right now, and I need to remember it. Okay, so you need to prepare for them. So I'll communicate all of this one. So only I'm missing one of them that I think is important for you guys to also review. Okay. So we're going to meet at 9:30. Right now it's actually 9:16. Sounds good for everybody? Yes?
Yes.
Yeah.
Very good. So I'm gonna pause I'm not gonna stop the recording, so please don't leave. So I'm gonna pause this stuff and I'll see you guys, and turn off my camera, and I'll see you guys in about 15 minutes. Again, welcome to the second part. The second part really deals with the lab. And you will see that the lab is really has a lot of stuff in it. I think on page 14 there is a mistake that we really need to correct, but it doesn't have any bearing whatsoever on your lab, but we need to correct that anyway. Okay, so let me minimize this window. Let me find the lab. According to this, we are in week 13. Okay, so let me open the lab in here. You open it in a separate tab, okay? Separate browser, separate window, completely different, so that we see what we have. Okay, let me share with you the screen. Okay. As I was saying, you have the response form only. I think I need to give you the actual instructions also, which is going to be a separate file, okay? So, but it should be, I think it should be self-explanatory in the sense that you should be able to get these things. The lab, and I'm going to refer to that, the lab includes a lot of instructions on how to deal with the, not a lot of a lot of reference to something that is from the Sham series. I know I'm not sharing. It's locked? Why is that?
Yeah,
Oh, 11 a.m. 11 a.m. Why is that?
Yeah,
Okay.
it's locked until April 12th. At
Okay.
11.
Okay, let me fix that. Let me make it. I don't know why it's like that. Can you guys see it now?
But now it says it's locked until 8 a.m. on the same day.
The 12th, then why is the 12th? I'm sorry. Okay. Let's make it today. Change. Today is the 5th, isn't it? That's why I got confused. No, today is not the 5th, actually. The week starts on the 5th. That's why it gets confused. It should have been on the 5th of this week. Now, can you open it?
Yeah, now I can.
Okay, very good. So I'm glad I'm doing that. Okay, listen, I'm gonna add another file to it. So let me edit it before I do that and add another file quickly in here because I think you will need that file. So let me save it somewhere else. File, let me save. It's gonna be a Word document file, so I'm not gonna really even bother changing it to a PDF file. Save as. And then I'm going to find a place where to save it as. So I can grab it from there, Spring, and it's in there. Save, come on. And let's close it, because if I don't close it, I don't think I can attach it. So here is the Word file. And I'm going to upload file, upload document. Let me find it now. Should be in this folder, I think. 2022 spring. And it's this one. I'm going to grab it and drag it in here and submit. I changed the name, that's all, because the name is kind of a, just remove the docs on it. It's a Word file. Done. And let me save it so that you guys can see what I have changed in here to it. Okay, if you refresh the window, the one that you're looking at, and let me share the screen now. Am I sharing the screen? Did you guys see all of these things? Yes? Are you looking at the file or not that I just uploaded? Or am I sharing something else? Let me stop sharing because I have no idea what's sharing in here. Share again. Yes?
Yeah, I can see it now.
Okay, earlier it wasn't, what screen was I sharing? I don't know. Any idea? Anyway, so here is the response file. This is your PDF, the one that you're going to fill. This is the actual file itself before the raw file. It's in Word file. And this is the zip folder that I told you about. Okay, this one, you need a Windows machine for it. Okay, you need a Windows machine for it. So let me open it. Okay, let me save it. And I think I already did save that. And once you save a zip file, you need to extract it. So let me do that just to show you how this works, okay? Does everybody see that I can save this file or not? Does the pop-up show or not? Come on, guys. Are you looking at the pop-up where I can save the file or not?
Yeah, we can see it.
Okay, very good. Because when you guys comment when I'm doing this, I can't tell. Okay, I already saved it in this folder. So I'm gonna go to this folder and share with you that folder so that you guys see exactly how that is. So I'm gonna stop sharing that. I'm gonna open that folder first. I think I did open it already, but just in case, let me open it again. So I'm gonna create a new folder so that you to see how it works, okay? And I know a lot of you probably are good with these things, but I just wanna make sure that you guys are know how to handle this type of work, okay? So I'm gonna go and share with you now, share. And I think this is that folder, the new folder I created. So when you download a zip file, it's just a file, but it's really, it has a lot of content inside. So if I click on this file now, what Microsoft does for me, it opens it. Depending on your computer, it might not open it, but for this one, you really have to have a Microsoft machine, okay? A Windows machine. So I'm gonna extract all, and it's telling me, where do you want to extract it? I'm going to extract it to the same folder for my case, okay? But you have to be really aware of where you extracted your file in here. Okay, so it's opened it. I don't know if it's sharing with me what it has opened, but this is the one that has opened. Okay, so when you extract it, it just extracts to a new folder. So now this is the folder, okay? This is a free software that you can download. If you don't have a Windows machine, you should be able to look at the software and I tell you exactly the link where you can go and find it, okay? And I probably will follow up with this one. This is the file that is of interest at this point, the executable file. If your computer complains and say, are you sure you want to open this file? This is from a website. This is a legitimate a file from basically Canvas, number one. Number two, this is actually, you can Google it and you see that PC Basic is not really a virus. So you have to authorize it. You have to tell it to open it. Once you open it, again, your antivirus might object on you running this file, or it might disappear altogether. I really did not try it with Windows 11. I have the laptop on Windows 11, but it works fine in Windows 10 machine. This is a Windows 10 machine. So again, I'm going to double click on the file. Here is, I don't know, do you guys see the pop-up that it says Windows protected your PC? Do you see it or not? Microsoft Defender.
I can't see that.
You can't? Okay, here is what's going on. An antivirus, which is in this case, I have Microsoft Defender on this computer, is telling me that Microsoft Defender Smart Screen prevented an unrecognized app from starting. Running this app might put your PC at risk. Please run it, okay? So it's telling me more info because the only choice I have right now is don't run. So if I click on don't run, I'm back to square one. Basically, I can't run it. So I have to click on more info. Once I'm more info, it's telling me the name of the app and the publisher is an unknown. It's an old app, okay? It's not gonna harm your computer whatsoever. So I'm gonna have the option to, now two options, either run anyway or don't run. So I have to really do the run anyway, okay? Now it opens two things. Let me stop sharing and share. It opened two command prompts. Don't close the other one. You have two of them, okay? You have this one and there is another one that is blank on the other side. Let me show you the other one. Stop sharing and share with you the blank one. So this is a blank one. Don't tinker with this one. Don't close it, because if you close it, you close the other one, okay? So this is just to get, this is the old DOS command, if you guys are familiar with it. So this is the command prompt to get it to do stuff, basic stuff from computer. I think we really need to update this software, but at this point, I don't have access to it, honestly, to probably rewrite it and put it in some sort of a new platform or something like that. Anyway, so the thing with it is, here is the file that opens. The choices are in the bottom: list, run, load, save, and everything else. So if you look at the instructions, so let me stop sharing. So I don't close this. At this point, it's open. It's in the background. So I'm going to go and open the instructions. Okay, so I'm going to open the Word document. Oh man, it opened it in the browser. I don't want to open it in the browser. I want to open it outside of the browser. So I'm going to come back again in here and share the Word file because it has all of the instructions already. Share the Word file. So first of all, it's giving me two die in this case. Okay, two dice and a dice, two of them. Okay, each one of them has 6 faces. Remember, we're doing probability now, trying to do because that's the basis of quantum mechanics. So each one has 6 faces, and you're going to roll it. How many times do you roll? Because you're going to roll them once. So in this case, you're going to have one of them either having the value of 1 on that face, the face up, and the other one on face value of 1. And the only way to get 2 out of them is both of them have to be on face up and up, which is 1. Okay. Or the first one could be 1 and the second one could be 2. In this case, the sum is 3. 1 plus 2 is 3. Or the first one. So all of this one is the potential possibilities for 1, and the same time the potential possibilities for the second one. So the second one, if the first one is 1, could be 1 or 2 or 3 all the way to 6. So the values in this case are going to be, the sum are going to be from 2 to 7. The first one could be 2 actually, not 1. These are all the possibilities for the first one. Then the second one could potentially be any of these values. So again, notice the sum of 3 is popping up here and here. So there are 2 ways for you of getting 3. there is no other way for you to get 2 with the exception of this throw. Okay. And again, so you could have a 2 and a 2, which gives you 2, 4, but you also could have a 4 in here too, 1 and 3. And the second one in here, a 3, and the other one in here, if you get a 3 out of the first one, the only possibilities are 1 through 6 for the second one. You could get another 4 in here. So there are 3 ways of getting 4 in here, either getting 1 and 3. The first I would get 1, the second one is 3, or the first one gets a 2, the second one gets a 2, or the first one gets a 3 and the second one gets a 1. So all of this amount to the same value, the same sum, which is 4. And the same thing in here, you continue doing that until you get all of the different possibilities. How many possibilities in here? You have 6 times 6, which is 36 possibility ways of basically combining these 2 different ones to get sums that go anywhere between 2 and 12. That's the maximum. If the 2 faces are up, 6 value, then in this case, the sum is 12. The lowest potential value is a 2, when you can end up with only both basically of them having 1 and 1. So those are all the possibilities. So the question here, what is the most likely sum? That is really the question we want to find. Okay, what's the one that repeats the most often? That is going to be equivalent to the average, if you wish, of all of this different measurements. By the way, this is related to the entropy when we had a discussion a long time ago about the entropy also, and this is the different ways of arranging the particles to get the maximum energy. So this is also related to that too. So this has to do with the different ways of getting the macro state out of the microstates. Okay, the microstates and how you arrange these things in here. Okay, so now the values that potentially you could get are 2 all the way to 12. The number of occurrences, if you count how many times you get to 2, it's only 1. The number of occurrences for 3, here is 1, and here is 2. So in this case, it's 2. The number of 4 is actually 3, and so on and so forth. The highest number in here is 7. 7, you get it 6 times. In every throw, you can get a 7. Here you can get 7 and 1 and 6. Here you can get 7, 2, 7. Here you can get a 7, 3 and 4. Here you get 7, 4 and 3. Here you get 7, 5 and 2. And finally, you get this through 6 and 1. So that is the most likely outcome. So if you throw 2 die, most likely the highest possible potential value is going to be a 7. Okay, that's the closest one because of this one. If I add all of these values, they give me 36. So this is the normalization, if you wish. Okay, so everything now is divided by 36. So all of these numbers, 1 over 36, there is a probability of 2.8% of getting the sum of 2, because there is only 1 outcome out of 36. Whereas there is 2 outcomes of 36 to getting a 3. So the chances of getting 3 are 5.6%, twice as much. They double. Okay. And you keep on increasing, getting 3, of course, is 3 over 36, which is 8.3, and so on and so forth. The highest potential, again, is for 7, is 16.7% to getting a 7. That's why that's the most likely outcome. I mean, granted, 13.9 is not far from it. So you could end up with a 5 or a 5. The sum of I mean, not the 5, 6 or an 8, the sum of these values in there, okay? Which is occurring 5 times in either case out of 36. So that's how the probability in this case. So when we sum up this values in here, they add up to 1 exactly, because it's 36 out of 36, and that is 1. So this is the normalization condition that we did on our distribution function. Remember that our wave function, because it's a distribution function also. So in the sense that we said that when we sum up the value from all the potential values that we have, from negative infinity for the case of one-dimensional problem to positive infinity, that probability, which is of a psi squared, need to be exactly 1. So that gave us a way of finding the value, the amplitude with which we were multiplying that psi, I'm sorry. So from that point on, that's a normalization condition. If we don't use a normalization condition, we have to divide by this number anyway to get the probability, because it's interpreted as a probability. Okay, what is the average value? Again, all we have to do is multiply x, which is this value by this probability and add them up. And of course, they should add up to the average value, which is 7 in this case. And that's exactly what it is, 7. So the theoretical outcome in here is 7. If we do an experiment, we might not find 7. We find probably a value that is slightly more than 7 and slightly less than 7. Obviously, if we repeat this process again, if I really have to die in here, and I do it again and again and again and again and again and again, probably 10,000 times, obviously going to take me probably 3 months on a row, not eating and drinking, just basically doing this. But if I do it that way, I can get the value of 7. Otherwise, I'll probably get this because there is a chance I can actually get both of them face up. The smallest probability in here out of the whole thing. Okay, 2.8%. I mean, if you go and play, what is that thing in Las Vegas, there is a chance that you might not end up with a 7. Okay, but it is the most likely outcome in this case, because at least it's the average value of all of the throws. But you have to do it really a lot of time to get that value. Typically, when we're looking at the standard deviation, we compute also the average of x squared. So the average of x squared in this case is 54.83. And that gives me then the standard deviation. The standard deviation is defined by the square root of the average of the squares, which is the RMS in this case, minus the mean, the square of the mean. So again, statistics and probability. So if you take the RMS squared in this case, because the RMS is actually square root of this number, minus the square of the mean, then in this case, this is your standard deviation, which is 2.42 in this case, okay? And the standard deviations, if you guys have taken probability, any one of you has taken probability of statistics class or taking it now or something?
Yeah, I have.
Okay, very good. Then in that class, basically what you will see is that if you go anywhere above the average by a value of sigma, which is what this thing in here is, okay, or less than that one by sigma, you are almost 2/3% of the data, meaning 2/3% of the data are in that zone. So how much value in here? We have anywhere between 2.42 added to the average and subtracted from the average. Subtracted from the average give me about 4.55. 4.45 doesn't fit any of these pictures, so it's 5, okay? And then 9.45 as the other number. Again, I cannot have a 9.55, I can only have a 9 in this case. So 2/3 of the data are between 9 and 5. 68% really, to be more specific, okay, of the data is in that range. If I add up all of these numbers in here, 4 and 5 and 6 and 4 and 5, so that is 15. 15 plus 9, that's, what's 15 plus 9? 24. 24 divided by 36 should be about 2/3 of the way, okay? That's how it should be, okay? Now, if I go to sigma from your the central, what is it called? The central, I forgot, the central theorem or something like that in statistics. If I go two sigmas, I encompass 95% of the data. If I go 3 sigma, I go to 98% or something like that. So at least 1 sigma will give you this much of probability, almost 2/3, actually slightly more than 2/3, 68%, okay, of the data. Okay, it's going to be between 5 and 9, okay? So, and in this case, actually, it's going to be 66% or something like that. Because 24 over 36 is it 36? Is it 67%?
It's either 67 or 68.
Yeah, something like that. Okay, anyway, so we are close from it. Again, you need to answer the questions. Okay, let me show you the report, okay, because it's important that you put the stuff in the report in there. Stop sharing. And let me get the PDF file also going. Okay. Share the PDF file. Okay, so this is the PDF file. Okay, permutation and combination. Combinations doesn't matter about the order, and permutations matter. So if I really care about which dice produced which one, then in this case, I have to be, this one is 1, this one is 2, or this one is 2, and this one is 1. So that is basically the difference between them. Permutation doesn't care about that. Okay. Anyway, so this is the same table as I repeated again. And you're supposed to, this is the same data as before. This is the same step as before. And then you're going to talk about the objectives of the entire lab. Okay. Let me get into this part in here. So we opened the zip file and we double clicked on the PC basic. And then when the second DOS, because there are 2 DOS open that open, okay, type in load dice with this quotation marks. If you forget the quotation marks, it's going to complain, okay, to load the application, and then type run, enter any number as suggested, and enter. Okay, so now let me stop sharing so that we can follow the steps. You have to do it in this order, okay? So I'm going to find that, share. So the first thing it says in here, it says load. Oops, I need to type in here, load. I think the capitalization doesn't matter, but let me try it because this is Windows anyway. You have to be careful if you're using if you're using another software, which you call it the another machine, it might matter. Okay, so it says okay, so it loaded it in the memory, and now we're going to hit run. Okay, so we're going to type run, and now it's telling me to enter any number between this much and this much, so I'm going to enter this number. Okay, so now we're ready. So it says how many, what's the value of D, what's the value of S, it's going to ask me, and then what's the value of N. So I need to answer all of these questions to be able to pick up the this things in here. Let me prepare basically the PDF file. You don't need to do this, what I'm doing right now, because I did some changes earlier to it. So I don't want to have these changes actually. But I want you guys to see the actual experiment because it's going to yield different numbers every time. And this is a randomizer. I was hoping to get, I don't know, I think sometime we'll have to probably change this program altogether. Okay. That's it. Those are the changes I made earlier. Anyway, so let me share with you where these numbers are coming because I need the dice, the number of dice, how many of them. And I need also the number of sites on each and every one of them. If you look at the lab instructions, see this numbers change. And then it tells you the number of trials that you can run. So I'm going to stop sharing that one and go and show you where the information is coming from. First of all, it's coming from this PDF file, which is actually the Word file also. So obviously D is equal to 2 in this column. So I'm going to put 2 in there. Okay. The maximum number of rows is 2 times 2, which is going to be 4. Okay. Because if I have on one side of the dice, I have 1, and the other side I have 2. And the other one also I have 1 or 2. The maximum I could end up with is 2 on both sides, and that's 4. Okay. So S to the power D is clearly 2 to the power 2, and that is also 4. So far, I really don't need that simulator whatsoever. I can just fill out this information in here. And then the same thing in here. This formula in here, the number of combinations. So these are the permutations. So the combination in here, the order on the dice doesn't matter. So it can have 1 and 2 or 2 and 1. It's the same thing. So in this case, it's going to be D times S minus 1 plus 1. So D is 2 times 2 minus 1, which is 2, which is 1 times 2. That's 2 plus 1. So that's 3. Okay. So in other words, I could end up with 1 and 1, which is one possibility, or 2 and 1, or 1 and 2, which is another one. Okay. So both of them are going to give me the same value, or it could end up with 2 and 2. So there are 3 ways of getting this one. So this is what I mean by permutation in this case, combination, I'm sorry. So in this case, it doesn't matter. Permutations in here is the order matters. Okay, I think I gave you the backward problem. In the permutations, then in this case, you have 4 ways. You could end up with 1 and 1, and there is only one way of getting it, or 2 and 1, or 1 and 2. Okay, that's 3 so far, or 2 and 2, and that's 4. Okay, so that's what these numbers mean. Obviously, when we're dealing with big numbers, it gets a little bit complicated to think about it, but use just the formulas in here. Then the average in this case should be D, which is 2, times S plus 1, which is 3. 2 times 3 is 6, divided by 2. So that should be 3. So the average should be exactly 3. That's the theoretical average, at least. Okay. Now I need the simulation, what the simulation is telling me. So I'm going to come back in here, and I need n to be 12 in here. So I need to put n equals to 12. So I'm going to stop sharing in here and answer those questions. So I have D is 2, S is 2, and n is 12. So I'm going to share the simulator. So it's asking me how many of them I need 2. Oops, I need to click in. I need 2 of them. How many sides each one of them has is 2. How many tries do I need? It says do 12. So I'm going to do 12 in here. And it gave me right away the value. First of all, the average is not 3. It's 3.333. And it gave me the standard deviation of 0.74536, whatever. I don't know if I can copy, but I can write this one in here easily. So I'm going to stop sharing. I'm going to go back to the PDF file and put these 2 numbers. The first one is, what is the average from the simulation? The average is 3.3333. It doesn't matter how many you retain in here. You can write them all. And the error, I'm going to come back to the error. Before I do that, I want this value from the simulation because it's giving me also for the standard deviation 0.7453565. Okay, so it gave me all of this number. I need to compute this number. If I compute this number, I have D, which is 2. I have S squared, which is 2 squared, which is 4, minus 1, which is 3. So 2 times 3. Wait a minute. Yeah, 2 times 3, which is 6, divided by 12. And so I will have 1 over square root of 2. And 1 over square root of 2 is 0.707. 0.7070. And that number is repeating. Now I need to find these errors. All I have to do is deduct one of these 2 from the other. Am I not sharing, or what's the question? Okay, sorry. Okay, so in this case, no, it's a known number. I'm sorry about that. It's a known number. 1 over square root of 2. It's the cosine and the sine of 45 degrees. Okay. So anyway, the difference between these 2 numbers is obviously 0.33333 divided by this number 333. So it's going to be, if I use a calculator, so I'm going to pull a calculator anyway. So let me get into this number in here, or maybe, hold on, let me see if I can open a new page in here first, a new insert. Oh man, I need to insert break page. Okay, so, and I'm going to do the math quickly. So it's going to be 0. And 0.33333, doesn't matter how many times divided by 3, it's going to be 0.111111. Okay, so it's 11.1%. So it's share. So it's 11.1%. Don't forget to multiply it by 10, by 100 to get the percentage, because it's asking for the percentage error. So it's 11.1%. 1 decimal point is good enough for this purpose. Now I really have to do the difference between these 2 numbers and divide them by square root of 2. So I'm going to go back to my calculator in here, stop sharing. So I really want to share that calculator because I want to do this precisely, because this is, I want to find this error. So I'm going to share. What is the calculator? I was using Mathematica for it, by the way. if I can find Mathematica. Here it is. Okay, so I don't know what this number is coming from, but let me try to erase it. So what I have in this case is, first of all, open parentheses. Zero point 7453565 minus, I know in here it's going to be 1 over square root of 2, so it's going to be 1 over, that's the advantage of using Mathematica, because I don't have to really even write that number, and divided by that 1 over square root of 2, which is going to be square root of 2. So I'm going to divide by, before I do that, I'm going to multiply by square by 100, because remember, this is going to be a percentage error, okay? And divided by 1 over square root of 2. I hope I didn't make a mistake in here. And shift enter. It's giving me an error of 5.409%, 5.4%. Okay, remember I multiplied it by 100, so this should be really 0.054. Okay, so I'm going to go back into my PDF file, and I'm going to write in here 5.4% error. Okay, I'm going to do the same experiment, but with 50,000. If you do 50,000, you're going to wait for a long time. So I'm going to start it just to show you. Share this, the same thing. And I'm going to wait for it and explain part of the things until it gives me the answer. So yes, I want to start again. And the number is still 2. And the number is still 2. But the number of tires now is 50,000. So it's going to be 50. So the computer is going to be super busy for a long time. So if I hit enter, this is what happened, okay? You're going to be there. So give it time. Don't give up on it, okay? Depending on how much CPU, I think I have 32 gig on this computer in terms of RAM. So depending on how much power you have in the computer, it might take a long time. So give it a time. So in the instructions, it tells you, please don't go beyond 50,000. And this is because we're using computers on campus. Now, if you're into some difficulty with this one, please let me know. And my suggestion is try to reduce this number instead of 50,000, bring it to like 40,000 or something, and see if it works for you. Or 30,000. Try not to even go beyond 50,000. This is ridiculous. I mean, it takes so much time. So I'm going to stop sharing and wait for it. So I'm going to pull it up so that I can see it when it gives me the answer, and share with you the instructions again, so that you see exactly what we're looking for. Share. No, not that one. Share the instructions. In the same time, I want to have that in front of me, so it will give me the answer. Okay, so here is the next one. You have a 10 die system. Basically, you have 10 of them, and each one of them has a 2 value in it. So you're asked to put a number in here. Please keep it reasonable. Do not put 500 or 5,000. That's too low. Try to go anywhere around 20,000 or higher. Okay, depending on the power of your computer. If you think 50,000 is going to be too long for you, then put it somewhere reasonable in there. Okay, 20,000, 23,000, 25,000. If you can do those numbers and the computer is working fine, it should be fine. Okay, you should not have a lot of errors. But if you notice that you have a lot of errors, then in this case, it's spewed the data now. So my computer finally gave me the answer for this one's in here. So at that point, you need to probably refrain from it. And if the error is too low, then you need to increase it accordingly. So I'm not really putting a limit in here how much you put, but I'm hoping to see anywhere between 20,000 to at least like 40,000 or something like that. If you can do 50,000, you will have the least errors, and you will see why shortly. I mean, this is the data I just came in. As a matter of fact, let me stop sharing that one and share with you the data that the program has given me. It gave me an average. Remember, it's supposed to be 3. Now it's 2.99668, which is very close from the 3. And it gave me standard deviation of 0. Instead of 0.077, 0.707, which is really 1 over square root of 2. Now it's giving me 0.706, okay, 84444. So now it's giving me actually a closer value than to the theoretical value. So I'm going to stop sharing that one, and I'm going to share. So that's the value of using a higher number, is that the errors will be minimized. So in this case, I still have 2. I still have 4. It's the same number. They did not change. I still have 4. I still have 3. So all of these things did not change. This one will be different, by the way. This one will be different in here. This one will be different, and this one will be different. Okay. The purpose of these two exercises in here is to determine that the higher the value trials in here, the more precision you're going to get. Again, this is the theoretical value. Now, instead of 3.33333, it's giving me 2.99668. Okay, and I'm going to compute the error very shortly. The theoretical value is still 0.70707, repeating all the time. And the simulation now is giving me 0.7068444. Okay, so I'm going to find the error in the similar fashion as I did before. As a matter of fact, I'm not going to change that one in there. So I'm going to stop sharing. I'm going to share the calculator again. So the square root of 2 did not change. It's this number that changes now. So it's not, obviously I need to take it in absolute value. Okay, so the error is going to be negative, but we're going to fix that one. So it's 0.68444. So I'm going to put this one a plus, and I'm going to change this one to a minus because I know the other one is higher than the other one, so that you can get a positive value. That's all. So if you get a negative value, just put the positive value. This is, you're talking errors now. You're not talking something that okay. So everything else does not change in this formula. So everything is the same. So this is the second part. So I should get a less error now than what I did before. And sure enough, this is a percentage. It's not 3%, it's 0.03% or 0.04%. Okay, when you round it up. So it's a 4/10,000ths. See in here, so I'm gonna do the calculation also for the other one because it was divided by 3, so it stays divided by 3. So in here, I have to find the difference between 3 and 2.99668. And times 100, just like the other one, just to get the error now in percentage right away. So the error now has dropped by a factor of 100, actually. Okay. Before it was 11%, now it's 0.11. So when the number of trials increases, you're getting more and more closer to the theoretical values. Okay. And that justifies something very important when we're doing quantum mechanics, is that actually, because especially when we're dealing with a large number of atoms, in the case of the solid, it really becomes just the statistics in this case. So again, the error now is 0.11, not 11%, 0.11, and this error now is 0.04%. Okay. So this column now is filled. All I have to do now is this 2 columns. Again, these numbers are easy now. This is 10. And now, what are the potential values in this case? You can have 1, 1, 1, 1, 1, 1, 1, 1. So in this case, is going to be, I'm sorry, what am I talking about in here? The minimum in here. I'm sorry, I'm talking about the minimum and the maximum. Yes, so the minimum roll is going to be, each and every one of those spaces is going to be a 1. So the minimum value is 10. And the maximum value in this case is going to be, the maximum value is going to be 2, 2, 2, 2, 2, 2 on every one of these dice. So it's going to be 20. Okay, is it? 2 added 10 times 20. Okay. In other words, this is D, and D is going to be 10, and this is D times S, which is going to be 20. Okay. Make sense so far?
Yep.
Okay, so it's straightforward. Then the number of permutations in here, and also the combinations using this formula and this formula, and finding the average, the theoretical average, and finding the theoretical standard deviation using the same formulas. Now going back into the experiment and running the experiment and getting the simulation and finding the difference between them, and going back also to the same experiments is going to give you the two values for the standard deviation and also the average. And you're going to find the difference between them. Don't forget to multiply those differences, I mean the errors by 100, because we want this in percentage already, okay? So if you're finding an error that is, I don't know, 17%, you're gonna find a 0.17. Don't try 0.17 in here, you're gonna write 17%, okay? Because I'm gonna check it, okay? So if you say, for example, you did it 5 times, you're gonna find a huge error. If you did 50 times, you're gonna find a big error too. Then in 500, you're gonna find a big error in here. 5,000, you start to get a thing under control. 23 times, 20. What did I do in here? 2, 3. Oh, this is maxing? Oh no. Okay, I need to fix this PDF file, okay? For some reason, it's maxing at 3 digits, okay? No, I can. Why is it not doing that? No, I can. It's working fine. Why did... I don't know what's going on with my computer. So this is 230,000. That's not acceptable, okay? But 21,200 and is fine, okay? Don't go more than 50,000. For a second, I thought that there is something wrong with the PDF file, but there is nothing. So again,
Wait, I have a question.
yes.
So for all the number of trials, you want us to go like 50,000 downwards for the rest of these?
Yeah, here and here and here and here. If you can
Okay.
get 50,000 and you're in good shape, your computer is working, you're in good shape. You're gonna get this errors way, way under control. Okay. But don't go be above 50,000, because if I want to double check your data, I can't. I mean, I don't honestly, it's going to take a long time just to check each column. And if each and every one of you is doing that, so it's going to be a long time for me to basically grade your stuff. So what I'm saying in here is try to put a manageable number. 30,000, I like it. 40,000, I like it. 50,000 is okay. And don't put 127,000 times, okay? That's going to be ridiculous. It's going to be probably an hour waiting for it to just spew the data for one of them, okay? So unless you really want to torture from me and torture yourself in the process, then put those numbers, okay? I like 20, 30,000, honestly. They're fast enough to give you and the errors are manageable, okay? Even if you get an error of 3% in here, and an error of 2% in here or 1% in here, it's still good, okay? So that's basically the bottom line. 30,000 is a good number. 40,000 is even better. 50,000, if you really have that time. If not, but don't give me something like 10,000 or 5,000. That's going to be too small. You will find a huge errors to begin with, as we saw it in here. 11% is too much. 11% is just for 12. Obviously, if I put more, it's going to be better. Make sense?
Yep, sounds good.
But this whole thing is straightforward. I hope that you guys have no difficulty with it, okay? And answer these questions in here as related. You're gonna take this die in here, this situation in here, 10 and 2. And you're gonna get the data for it, okay? What I mean by the data, let me stop sharing. No, Natasha, okay? If you do that, I'm not gonna grade it, okay?
I'm only kidding. We're not gonna do it.
So let me stop sharing. Let me show you where you get the data for this part in here, okay? Share. Again, the same thing in here. I'm gonna do the 10, so I'm gonna say yes again. I'm gonna do Oops, I need to click in here. Why is it not clicking? Yes, not you. Okay, so the number is 10 now. The number of phases is 2, and the number of trials, just to keep it manageable, I'm going to put 500, okay? So that he can get the data quickly, but this is not what I'm going to do, okay? For this, the second part in here, okay? So it's 500, it should give me data quickly. Okay, so I have, for 10, I have 0 occurrence. For 11, I have 3 occurrences. For 12, I have 17 occurrences. And for 13, I have 56 occurrences. And for 14, I have 119. For 15, I have 130, and then it starts to decrease. So I'm going to stop sharing that. This is not the data to use, okay, so that you guys know. You need a much higher number than this one, okay? Let me find the, so that I can see it. So I'm going to copy the data that I get. I got 0 here, okay? Obviously, this is not what I should get, but this is 13, 17, 56, 119, 130, 87, what is it, 47, 35, 6, and not a single occurrence of 20. Obviously, this is going to be a 0, the probability is 0, and this is going to be 0. I need to add up all of these numbers, okay, and put the total in here so that I can find the probabilities in here, which is this number divided by that total. So it's a good idea to get Excel going at the same time, okay? So, I mean, you guys know how to add this number, so I'm going to do that again. So it's 0, I don't have to write 0, 3 plus 17. I mean, if you can do it on a calculator, also you can do it on a calculator. So it's just summing the numbers in here, okay? 56 plus 119 plus 130 plus 87 plus 47 plus 35 and plus 6. I'm sorry. Wasn't that supposed to be 500? Those are supposed to be the sum, okay? I didn't have to do that. I'm sorry. My brain is not functioning right now, okay? Blame it on food, the fact that I'm not eating, but that's another story for another day. Okay. It's not for diet or anything else, so that you guys know. Okay, anyway. So now this number is actually what you put in there. That's the number of trials, okay? In here. And this number should be 1. If you don't find it to be 1, we have a problem in there, okay? So now all I have to do is 3 divided by 500 in here. So I'm going to find 3 divided by 500. We can do it quickly, which is what?
DJ, are you sharing your screen right now? Because we can't see it.
Okay, I'm sorry, I'm not sharing that screen. So I put the data in here. So this sum is 500, okay? Because this is the number of trials you did. And the number of trials, the outcomes were 3 here, 17 in here, 60, 56, and so on and so forth. So this is, since I put 500, is going to add up to 500. That's what I was not thinking about, okay? So this number in here, if you put 50,000, you should have 50,000 in here, okay? If you have put 37,420, you should get 37,420 in here. Now I take 3 divided by 500, and whatever that answer is going to give me in the calculator, so that's going to be the number, okay? So it's going to be 0.006% or something like that. 0.6% or 0.006 is another 0. Yes? Yes, no, maybe. This is 0.034.
Yeah, the first one is 0.006. Yeah.
And the third one, this is my data, okay? So this is not going to be the case for you guys. You're going to get a different higher number in here, okay? Put at least 25,000 or 23,000, whatever you like to do, but at least as you get fast enough data from your computer, because you need to match this curve. This is a Gaussian distribution, okay? And you're going to include the curve actually with you too. So you can actually do it in Excel faster. You can graph the whole thing and include your graph in there too. So it's going to be 0.1. Okay, you got the picture. 1, 2, or something like that, and so on and so forth. Okay. Do it. I think it's wrong in here. Anyway, I assume that you guys can do this division and give me the fractional numbers. So the sum of all of this probability should be 1. Make sense? Make sense so far?
Yes.
Okay. So I assume that you did that and you checked the normalization in your reply. Would you say that the data points match with the theoretical value? This is the theoretical value. It should be really a Gaussian distribution. And this is why, by the way, the Maxwell-Boltzmann distribution was used to begin with a long time ago. Even in this case in here, it leads to that. And so that's the theoretical. Depending on how much value in here you put, you're going to get it very, very close from it. Okay. So, and now this is the probability in general, how we introduce it. So this is the sum of all the probabilities from the minimum value to the maximum value should be 1. In discrete summation, in the case of continuous, we just convert the sigma into an integral. And the same thing, the average now is you multiply by x and the probability of each and every one of them, and you get, in this case, the average. The same thing, the average is defined in the continuous distribution using this definition of the sum, namely the sum becomes an integral. The same thing for the square in this case, which is the average of the square. In this case is going to be this value. And sigma is divided as the difference between the average of the squares minus the square of the averages. No, the square of the average and the average of the squares under the square root. Okay. The Gaussian bell-shaped curve, the one that you have in here actually, is given by this function, where mu is the average and sigma is the standard deviation. Sigma is this value and mu is that value. Okay. And the factor of 2 there is needed for the normalization, because if I take mu, if mu is 15 and sigma is this number, then we would have the plot as shown in this table. This is actually the one. Okay. So this number, the average is 15, whereas sigma is this number in there. And this is actually what we should end up with. The average should be 15. And the sigma for this distribution should be this value. If you do it high enough, we do it with extreme high precision, this is your value for sigma that you should find, 1.581, because it approaches a Gaussian, whose average is going to be 15. Then we would have that plot. However, this distribution has not been normalized because this A is not, I mean, the sum in here depends on A. So if we want it to be normalized, we impose on that sum, because this is how the sum is in terms of sigma and A. It's going to be equal to 1. So that gives me a value for A. And from here, which is just the inverse of this number, then if I add up all of these things, the average them with X is going to give me mu. This integral is easy to carry out, by the way. You don't have to deal with the sigma functions and the gamma functions or anything like that, because x dx is dx of x squared divided by 2 or multiplied by 2 in this situation. And this is actually x squared shifted by a value of mu. So if you do that change of variable, you're going to get the value of mu exactly in this case. Okay, and that's the whole point of it. Mu is 15 in this situation. Okay. The average of the squares, again, if you do this integration now, requires that integral that we did a long time ago when we did chapter 18. If not, it's also included in this lab too, toward the end of as an appendix, as an index. What am I talking about? I'm sorry, guys. Okay, my mind is completely out of commission today. Sorry. So again, you're going to get this integral in here. It has to do with the square of the standard deviation and the square of mu squared. obviously, if you look at the way that the value in here is written, this is sigma, this is the average of x squared, and this is mu squared. So if you square this expression, you're getting sigma squared equals to the average squared minus mu squared. Move the mu squared to the other side, and you have this expression because this is x squared is equal to sigma squared plus mu squared. Okay, that is, if you wish, how we can find sigma. Sigma itself, the standard deviation, is just the average of the squares minus the square of the average under the square root. So it's the same expression here rewritten again, that's all. But you can show that that's actually where this is coming from. You can do the actual integration in here and yield you that number, okay? Which is exactly what I'm talking about in here. Sigma squared plus mu squared minus sigma squared minus mu squared, so that cancels out. The end of the delta gives you sigma. Okay, here is where it gets a little bit, where we need that thing I was talking about in terms of the Sham series for the tables of integrations. In the old days, we do that. Now you can just Google any integral. You should be able to find integral tables for you guys, because all of these integrations are finite. In this case, it's from -1 to +1. In this case, from 0 to infinity. And in this case, from -infinity to +infinity. You should be able to get these integrals quickly, okay? If you have access to a Mathematica or an integration software like the one I have in here, you should be able to get those integrations also. If not, you should be able to get it to a simple enough form. And if you have difficulty with these integrals, please let me know. In other words, you're going to do the same thing for this kind of distributions. This is a polynomial distribution in this case. This is another combination in here. And you're going to find the normalization constant A for all three of them. And you're going to find the average, basically multiply this by x, and you integrate it after you normalize it. And you're going to find the average value. You're going to find the x squared, the average of the square, multiplied by x squared, and you integrate from the domain again from -1 to +1. Delta is defined as such. And you're going to get also the square. And you're going to take this minus the square of this under the square root, and that should give you the standard deviation. And you repeat the same steps in here for this kind of distribution and for this other distribution, okay? And again, there is a theorem in probability and statistics. If you have difficulty with it, let me know and I will direct you to it, okay? This is, what is it called? Triangle or something like that. I forgot the name for it exactly, but it's actually in the books of probability and statistics. Which brings us to our problem at hand, which is really Schrodinger's equation, that it's actually a probabilistic wave mechanics. This is the classical wave, for example, in the case of electricity and magnetism. If you do the transformations, you end up with a wave equation. And this has the dispersion law that we talked about, that k squared is proportional to omega squared, but we don't want that. We want omega to be proportional to k squared. And these are the de Broglie, basically, conditions that we talked about, the momentum as a function of lambda, and the energy as a function of f. And you can express also all of the things terms. Now with the relativistic corrections, you have this term. So at the end of the day, when we do the wave substitutions, we end up with again, this is the wave equation. And we end up with Schrodinger's equation, okay? If you want to read through it, if not, just basically skip to equation 13. And the time independent Schrodinger equation gets rid of the time by making this substitution. And hopefully you guys, this is chapter 40, by the way, this is part of your exam review. And this is Schrodinger's equation. Verify that equations 13 and 14, simplify to equation 15, just by substitution. Basically take the time derivative of this expression. The I cancels the negative I in here. And the H bar cancels the H bar, and the En comes out on the other side. Times psi, and the exponential drops from both sides. Okay, so this is easy to show. The connection between that and the probability that we've been talking about, the first part of the experiment really, is the fact that this is actually a probability distribution. This is actually given by that same game, basically, of throwing dice. Okay, so let us consider example 1. So for the case of the harmonic oscillator, this is the potential. So we go back to the potential energy. And over the domain, the ground state is actually given by this function. So it's a Gaussian distribution. This is for n equals to 0. Remember, the harmonic oscillator has n plus 1/2 times h bar omega. So for n equals to 0, it's given by simply this one. For higher values of n, it becomes polynomials times this exponential. So it's always decaying as you move away, because in classical harmonic oscillator, it oscillates between a maximum value and a minimum value. In the case of quantum mechanics, it oscillates between negative infinity and positive infinity, but it drops as an exponential to a negative x squared. So in a sense, this controls its behavior, okay? And brings it back, and the limit when h bar is 0, brings it back to the classical harmonic oscillator, okay? So the points where the harmonic oscillator, the classical harmonic oscillator, basically maximum and minimum are called turning points. And the turning points also reappear in here. This is when the mass will turn. So as the spring was extending, and it stops and returns back to compression. So those are called the turning points. And again, in the opposite direction, compression, stops and starts to go back in the opposite direction. Anyway, so this is basically where the values of E naught in here is. This is for n equals to 0, by the way. That's why you have the index of 0 in here. And the energy level is 0. Remember, it's n plus 1/2 times h bar omega. So when n is 0, this expression becomes h bar omega, where omega is the same value from the classical harmonic oscillator, square root of k over m. Okay, namely k is equal to m omega squared, because omega is equal to square root of k over m. So when you do the normalization again, then you can actually use this equation that was given to you a long time ago up there, or the one that I handed to you a long time ago when we did chapter 18. Or again, there is actually in the bottom of this this lab, in the index, at the end. I mean, my mind is really not focused. I'm sorry. So anyway, there is actually an attached part in here. Let me share it with you. Here. Yeah, appendix. What am I talking about? That's correct. I said it right. I'm sorry. So this is basically the one that I was talking about in here. And at the end, you get the square root of this is basically where you have all of this units back to x squared. So in order to get this value from it, in order to use it really, you have to include beta in the definition of x. So to make a change of variable so that beta x is y, and then dx becomes a function of beta, and all of the others will come out into the constant times the constant a squared. And now you can use that integral from negative infinity to positive square root of pi. So you plug it in, and that's what the pi comes in into the expression, square root of pi. But don't forget that's a squared. So when you take the square root of the square root, that's a to the power 1/4. And that's basically where this expression is coming from, the normalization of that condition. You can find the x to be 0, the average to be 0, and that is because it's an odd function. And you're integrating it from negative infinity to positive infinity. So the negative side will contribute the same amount of the positive side, and they cancel out. So the average is 0. The harmonic oscillator in quantum mechanics spends most of its time, in this case, on in the center, because that's where the average is. In classical mechanics, spends most of the time on the turning points, because that's when it slows down, stops, and then speed up. So it's moving slower until it gains enough speed. So it spends the least time in the center because it goes moving through it with extreme high velocity. That is when the kinetic energy is the highest. So the situation is reversed actually between classical mechanics and quantum mechanics when it comes to the physical problem. This is the square again. You do the integration. Now, when you plug in x squared, the function becomes even again. And you do it by parts. And I think I shared with you that file a long time ago from chapter 18. You can find it useful in here, the Gaussian distribution. And you should be able to use that too. We did that to find the RMS value for the velocity of the particles and stuff like that. And the math is similar. The applications are different. This is harmonic oscillator in this case of quantum mechanics. That one for the velocity distribution for particles in classical mechanics, basically in a box. That's the gas, basically, the ideal gas law. So the math is identical. And you can find the value of x squared. The only thing in here is that you have to shovel the values of x squared. Now the delta x is just square root of this number because this one is 0. Okay, so it's going to be the RMS exactly. Okay, verify that equations 16 are correct. These are equation 16, all of them. Okay, so I hope that you will not have difficulty with these calculations. Now we go back to Schrodinger's equation, and we have this situations. We have the infinite square well. We have the hydrogen atom, ground state, basically one-dimensional problem, a version of it. This is the potential. And the potential is, of course, zero. This is a free particle in an infinite square. So the potential is zero inside the square, inside between 0 and a. And outside should be an infinite value. So inside is 0 and outside is infinite. And this one, because this is really typically is a radius, and radius varies from 0 to infinity. It cannot be negative. So this is the range for this one, the domain for this one, I'm sorry, I should say. This is the different energy levels in here. I'm missing an m squared in here. Sorry, in the denominator, okay? Anyway, this is another type of potential, which is a finite smooth well given by the Koch, okay? The hyperbolic cosine function. In other words, it's going to 1 over Koch, I should say. The Koch blows up on both sides of the I, basically on x going to negative infinity. The Koch itself goes to a positive, positive infinity, and at positive infinity also the exponential dominates in the Koch and also goes to zero, to infinity. But then taking the inverse of that, so the particle in this case is going to encounter a well. Okay, I'm sorry, is inside a well. Because at both positive infinity and negative infinity, here is a potential, by the way. I should really have talked about the potential, not the wave function. The potential itself has this Koch squared, okay? And it has a negative sign. So on both sides, it's 0. On the between, it's a finite value. Actually, when x equals to 0, the Koch is equal to 1 plus 1 over 2, 1 plus 1 over 2, which is 1. So it's going to be negative u naught. So that's the depth of the well. So it's finite. It's not going to a negative infinity, unlike the first case in here. Okay. The math is a little bit more complicated, but you should be able to get this Koch squared. And if you have difficulty with them, please let me know. Okay. Again, with a good integrator, you should be able to get all of these integrals. Again, this integral in here should be fine. You should get the normalization function because you're given psi naught. So all you're caring about really is not this much in here, but you're caring about the integral in here by of the function itself. So you integrate this value after you square it, of course, because the probability function is this number squared. So it's going to be a squared times x squared exponential of a negative 2x over ad. And in this case, it's going to be a squared sine squared. And in this case, it's going to be a squared divided by Koch squared, okay? So you should be able to get all of these integrals in here. When you do the value of the x, you multiply this one by x, and you find the value is going to be an odd function. So, but it's integrated from 0 to a. This is from this is the one that is going to be 0. Okay, because you're integrating from negative infinity to positive infinity. This should give you a value in terms of ab. Okay, and the reason why in this case, I'm sorry, I said something stupid earlier. Because this is actually a well-defined wave function in this case. So it's just the ground state, I should say. Okay, this is in terms of n, but these are the ground states in this case. Okay, and this is the ground state and this is the ground state. That's why we don't have n in here. Okay, so we're just dealing with the ground state for this too, but this one is actually all the wave function psi n. Anyway, so you should be able to do all of these integrations, x squared, and delta x, which is just the square root of this number minus this number, and you plug it in here. I mean, I know the work is a lot, but is this manageable, at least in principle? The principle, I'm not talking about the details. Do you guys understand the process at least?
Yes.
Okay, very good. Anybody else?
Oh, I thought I already said yes.
Okay. I'm not looking at the chat, so if you put something in there, I'm sorry, I didn't see it. Anyway, the point being in here, the idea is basically just once you reach the integral form, then it's somebody else's problem. Then you can Google it and find somewhere else. Okay. Okay, here is the problem. I think this is the problem. Okay. We usually deal with LZ, and I know I shared with you guys the calculations for LZ in the case of the spherical coordinates, and you saw that it has related to ML in this case, the magnetic quantum number. Okay, and this is Lx and Ly. As I was saying before, there is an uncertainty about the values of the projections of the angular momentum along all of the other directions. So because of the uncertainty, Heisenberg uncertainty, so the only thing you can know in quantum mechanics are one component only and the length of the vector, the angular momentum only. So these two values have no meaning. If we're focused only on one direction, we typically take that direction to be the z-axis. If you choose to call it the y-axis, so be it, then the other two become irrelevant, okay? But when you do the transformation to the polar coordinates, I mean the spherical coordinates, the z direction actually is preferred also direction. So then it connects to the z component of the angular momentum. That has to do with the derivative with respect to phi, okay? So that's why, please ignore all of the other components of L in this case. They're irrelevant. As a matter of fact, the whole calculation here for the angular momentum is not going to be relevant for your lab at least, but for your general education, yes. Okay. What I mean by that is you have the Cartesian coordinates. This is where we start from. We have the polar, sometimes called cylindrical coordinates. You have r cosine theta for x and r sine theta for y, and then you have z cosine z by itself. Z doesn't change. I think in this thing the angles are flipped for the polar coordinates, for the spherical coordinates. What I use theta is used phi in this lab, and what I use phi is theta for it. Okay, but it doesn't matter. The calculation should be straightforward. You should be able to get px. Px and py and pz are written this way because of the fact that I'm using x and y and z in this coordinate state. In the phase space, and I'm going to just give you a little bit of background. In phase space, you use the coordinates of the particle. They are called the q coordinates, and the p coordinates are actually the momenta. Okay, so q and p. And when we move to quantum mechanics, that representation now is called the space representation, where everything else stays the same in space, and the p now takes these differential forms. In the momentum representation is the other way around. The momentum stays as is, and this becomes operators. So we're not doing that. We're sticking with this one, and this is actually the standard way of this. Is most of the textbooks, they do this approach. Okay. So, but just to give you a comparison with classical mechanics takes either. Okay, doesn't have any preference. But because this one changed into operators, then there is an easier way of doing it than the other. Okay. So again, I'm just giving in here the potential instead of function of x, y, z, and t. I mean, we normally don't have t in it, although we could. Okay, like in a magnetic field that changes with time, for example, you're trying to find the coupling with the magnetic field, the splitting, the Zeeman effect, for example, then that energy becomes time dependent too. So the potential energy. So they all become operators, but now instead of x, y, and z, you have r theta and z, or you have r theta and phi. Again, as I was saying, all of this discussion here honestly is not relevant for the rest of your lab. Okay. Again, for this question, Schrödinger equation. This is from chapter 43, by the way. We're moving now to higher dimensions. Schrödinger's equation, which is way up there, is becomes just this operator, basically. What is H? H is the kinetic energy plus the potential energy multiplying by the function psi. Except the energy in this case is written as an operator, where T is just this kinetic energy term, which has all of these things. This is the kinetic energy of translation in this case. This is called the Laplacian, by the way. This is the in Cartesian coordinate system, plus the potential energy. Potential energy most of the time in here just replace it by its value. That's it. So all you have to do is take this T and add to it this potential in either case and multiply it by the function that changes, the wave function that changes dependency. Initially, it was dependent on X, Y, and Z and T. Now it's dependent on R, theta, and Z in T, or R, theta, and phi in T. So that's the new function. And basically, you just symbolically rewrite the function itself. That's all. So you're not going to do the actual math. You're just going to sub the values in here for this question. So now, the harmonic oscillator, if you want to find the average of the momentum, remember the momentum itself is this expression. P sub x is this expression. Since this is a one-dimensional problem and time independent, so the straightforward, the partial derivative becomes just a straightforward derivative. And the function in the ground state is given by this expression, A times this exponential. So let me share with you where that the whole thing is coming from. Share. Where is that, my notes? To find them in here. Okay, so this is a side note in here. So in the same fashion that we were finding averages of psi star times x times psi times dx from the domain in here, whatever the domain may be. In the case of the harmonic oscillator, is the conditions, the bounded condition, which is negative infinity to positive infinity, actually. So this is the average of x. So what I'm going to do now is the average of p, the momentum itself, in the x direction, because it's only a one-dimensional problem, so it's only one p. So negative infinity to positive infinity, and psi itself is a real number, so I can just write psi by itself, times, in this case, the momentum operator times psi dx. But the momentum psi in 1D is going to be now equals to h bar over I times this straight, because this is, everything is independent. The only variable that I have in this problem is x now. That's why I'm changing the partial derivative into straight derivatives. Remember, psi now in the ground state is some constant a times an exponential of some number, which is, you can find it in it, times x squared. Okay. So now if I plug in this value in here, where a has been normalized, so you have already the value of a. So it's going to be a squared, because this one has an a and that one has an a. So it's going to be an a squared, the integral from negative infinity to positive infinity, that exponential of that constant times, and that h bar over I that comes in here is going to be equal to the derivative with respect to x of an exponential of, again, negative p squared beta squared x squared times dx. In other words, I really have to take this derivative first and then multiply it by the other exponential and then integrate. So if I take the derivative of this guy, it's going to be minus 2 beta squared x times exponential of negative 2 times beta squared x squared dx. And then back into that Gaussian integral again. Okay, albeit in this case, it should give me a 0 value for this particular thing. Make sense how this thing is? Because the momentum has this dependence on x in here in this representation. So if I go back into the lab, share, I know it's getting long in here. And I told you guys, it's not going to be a, so everything will be the same. So when you take the derivative in here, it's going to drop a beta squared times x. Oh, there was a factor of 2 in here that I didn't try, that cancels that 2. So everything is going to be a negative infinity to positive infinity of this odd function, which is going to be 0. So you don't even have to do this integral. Okay. Now for x squared, you have to take the second derivative. So h bar squared over I, the whole thing squared. So it takes it out, it's going to be negative h bar squared. And a squared is coming from that normalization that was defined way back, I think, equation 16. And now the integration is going to drop another x twice, 2 times. So it's going to have a beta x squared minus beta squared times beta squared x squared minus 1. So if you take this derivation, and it's going to give you this value. So the angular momentum now is going to give you 1/2 of m omega square h bar. Okay. And that's expected because that is actually the standard deviation now. Okay. We're going to repeat the same calculation now. Okay. But now for the momenta. So this is the infinite square well. And we're going to find the average. In other words, don't forget that you have a sine pi n pi x on one side divided by a times h bar divided by I times the derivative of a sine. So the derivative of sine is going to be a cosine, and you will end up with a 0 again in here, because the integral of a sine times cosine is going to be a sine of twice the argument, and between the boundaries of 0 to a, it should be 0 in here. But the square, which is the second derivative of the sine, will become a sine again. So in this case, it's not going to be 1, and the delta px should be a different value. Now you take this delta px that you find from here, and you take this delta x from this expression that you find from the previous table. Here is delta x, and you multiply by them by themselves. Delta x times delta p, and you should find a value for that product, and should be within the Heisenberg uncertainty relationship. This number should be greater than or equal to h bar over 2. If it's 3h bar, you're in good shape. If it's 2h bar, you're in good shape. If it's h bar, you're in good shape. Okay. So the product of these two numbers need to be greater than or equal to h bar over 2. If it's h bar over 2, you're in good shape. Okay. But remember, where you get this other delta x, it's from the previous table on the previous page. Right now we're on page, I forgot what page number is this. It doesn't even show me the pages. Page 16. So you need to go back all the way to page 13 and compare the delta x you get from this page and multiply it by the delta p you get from this page. And now you're checking the Heisenberg relationship. You're finding the square of this value, which is here, divided by 2m. That's your kinetic energy. You're finding the potential in this case, which should be 0, because remember it's 0. So when you average 0 between 0 and a, is going to be 0. And the total energy should be just that of the free particle, which is just the kinetic energy. Okay. You do the same calculation now for the hydrogen atom. You find px, and again, this is the one that should be a, don't forget that you're going to drop a negative, you have an x already in here. X times the exponential, and you have a derivative of this whole thing with respect to x. So you'll have several terms in here to work with them, but it's just an exponential now. It's really not hard to do this one, okay, to find px. But don't forget you have that derivative. If you want to find px squared, you're going to, again, take the second derivative of this expression multiplied by this expression itself, okay? And the integration from 0 to infinity, and find delta px. Once you find delta px, you're going to multiply it by, from page 13, this delta x. And again, it needs to satisfy Heisenberg relationship, Heisenberg intensity. In a sense, it should give you a value that is greater than, or at worst, equal to h bar over 2. Okay? You're going to find the value in here. And the same thing for px squared. Now, you have found px, so you have to do it divided by 2m. And you do the same thing for ux. Now, ux has this 1 over x in it. Okay? And 1 over x cancels this x from the calculation, and you will end up with, remember, you square this number, so there are 2 of them, x squared twice, okay? Because you have psi squared. So x squared divided by x cancels, and you will end up with an integration now for just x, which is actually, no, I'm sorry. There is another value. I'm saying, so this is a new integral. This you didn't do before. And add the two, now you have the energy. And you come into the last one in here, the 1 over cos squared, and you do the same calculations. Is this in principle doable?
Yes.
Okay, very good. I know it's lengthy, and I know probably you're not going to be too happy at the end of it, but I'm hoping you learn from it. The question has to do with the Heisenberg uncertainty. You need to verify that all of those values are greater than or equal to h bar over 2. If they are not, then okay. And then you're going to draw your conclusion. Here are the appendices that you need to see them. Okay. One final note. I promise this is the last one, unless you guys have questions.
Pinky promise? No, I'm kidding.
So how to close this thing? Okay, if you try to close it from here, it probably is not going to close for you. So I'm going to stop sharing. So the easiest way, I figured it out. Okay, you can go to the info. Once you go to the info, there is an option there to close the program. Let me show you what I was talking about. If you choose, where is the, it's not giving me even, list, I think list. I need to click inside. List. Oh, no, can I do no first? Okay, so we're done with this one. So list. No, that's not the one. I'm sorry. Anyway, I think I found it earlier, but is it screen maybe? Or key? No. Screen? No. Anyway, forget about it. Let me show you the short way of closing this thing in here, okay? And that is go to the other one that is running behind the scene and shut it down. That's it, closes the first one. Okay, now it's setting your screen sharing is done. So that's the easiest way I found it. The other one that is running behind the scene, the DOS command, really, the one that is doing the stuff. When you close that, it closes the one that you have in there. Okay. Sounds good, everybody?
Sounds good.
This lab, I promise to be something to help you understand quantum mechanics and actually have a better understanding of those things that we did in class, because it delves into all of those calculations and the meanings of those things and everything else. So I'm hoping that you guys have access to a Windows machine. If not, you can go to the college. Oh, but then the college, you have a problem. You have to borrow a laptop from the college, because you need IT to put that stuff on your computer. I don't know if it runs on I think it runs, I don't know. But in the lab, in the physics lab, we have that program installed on the machines themselves. So if you guys have difficulty, please let me know ahead of time. If you want to go to the lab and see if the lab technician is going to be available for you guys, and you can go and use one of the computers in the lab. Sounds good?
Sounds good.
Very good. Everybody, please, there is no excuse for not doing this lab. It's really a very good lab. It should help you. And if you have any questions, do not hesitate to ask me. And I'm hoping that you learn a lot from it. And again, we will not see each other on Tuesday. We will not see each other on Thursday. Thursday, you have your exam too. I promise to send you communication tonight, or hopefully if I do send it, everything is fine. If I forget, one of you guys will need to remind me and said that I did not receive about the focus of the exam, because there is another item that I forgot. Okay, I forgot right now, but I think it's important too, so that you guys have an understanding of that. And I will see you guys on the 19th.
Thank you. Have a good day.
So let me